let me just say a couple of things about what we're going to do today. So this is it's an overview course that I've been meaning to put together for a while, and finally did actually only a month or so ago, and then gave it to some people in machine learning. So you're the second guinea pigs. Although it's really organized as a three lecture thing, and you'll see 2/3 of it. But I think that'll be coherent, approximately coherent. And I know that there's some of you who've had a course on convex optimization. Like, how many would that be? So, yeah, so a fair number, right? And then, all right, so some even from me, I think. And I can reassure you that actually nothing you'll see here you've seen in that course. So, I mean, it's the same topic, of course, but so you don't have to worry about seeing the same thing. Or it's not the 10-week course compressed into one afternoon, right? So it'll be a semi-coherent thing. Let me say a little bit about what it's going to, how it's going to go, just so you get your expectations set right. So it's going to go like this. The first 20, 30 minutes is going to be almost non-mathematical. We're just going to talk about optimization, what would you do with it, why would you do with it, that kind of stuff. Very high level. And in fact, if you could go into a little bit of mathematics withdrawal. We'll go for a while. I'll show some examples. Then we're going to have a break. So maybe an hour, 10 minutes in. We'll have a break, we'll come back, and then your withdrawal is going to be satisfied. So your mathematics withdrawal, because we'll actually look at some stuff. We're not going to cover, there's all sorts of interesting topics we're not going to cover, because the idea was just to take out a coherent bit of stuff. And I'm going to rant and rave about various things at various points, and you'll see what they are. So there'll be a message. So, okay. So we're going to go ahead and start. I should say that putting a lot of this stuff together, and we'll see specifically what I'm going to talk about later, this was is stuff done also with Stephen Diamond, who's a PhD student in computer science at Stanford. So, okay. So we're going to go ahead and start. And so in this first lecture, what I'm going to do is we're just going to talk about optimization. Like, what is it? Why would you do it? What is it good for? Which problems can you solve, actually, and all this sort of stuff. And then we'll look at a special case, convex optimization. That's what this is about. And then we're going to talk about things like solvers and modeling languages. So we'll go into that. We'll talk a great deal more about modeling languages in the second part of this. Then I'll just show you some quick, simple examples, just so you get a rough idea of, like, what can you actually do with this. And then I'll wrap up, and then we'll take a break and come back. But this part of the lecture is going to be almost non-mathematical. So we're going to start with just what is optimization. Well, it's a problem that looks like this. Your job is to choose this vector x. That's a variable to be chosen, and that's you have to choose that, and there are constraints, and the constraints must hold. That's the semantics of an optimization problem. And the constraints are that there's some equality constraints that have to hold, and there are some inequalities that have to hold. And then among all the x's that satisfy these constraints, you wish to minimize this objective here, right? And there are many variations on this. You can, instead of minimizing a function, you can maximize a function, and whole fields are typically arranged to maximize or minimize or something. In economics, you might maximize utility or something like that. But they're easily transformed into each other, so it's not a big deal. And I should also say that real problems really have multiple objectives. And again, if you understand one of these, you understand all of them. I mean, if you really understand one. Right, so, okay. So what I'm going to do first is we're going to talk about, like, why would you optimize? What would you do with this? Well, in the simplest and most direct interpretation, x represents an action. It's actually something that you do. So it could be, for example, these could be trades in a portfolio. X3 could tell you how much of some asset to acquire or something like that. It could tell you that your left inboard aileron should go down 1/10 of a degree in the next 20 milliseconds, for example. So it's something you actually do. It could be a schedule or an assignment. So it could actually be an assignment that tells you which crews should go on which airplanes at which gates and all this kind of stuff, right? Or something like that. It could be resource allocation. So you could have a data center, and it could say which of the many jobs running, how many cores should each one be allocated, how much bandwidth, how much memory, these types of things, right? It could be how much power you assign to different wireless transmitters, for example. It could actually just be a transmitted signal, right, where you're actually deciding what you're going to transmit and then transmit it, right? So this is what X might represent, but it's an action. Now, in these cases, the constraints, they limit or they impose conditions. They either limit what you can do, right, or they impose constraints on the outcome, right? So that's typically what a constraint does. It could, for example, in resource allocation, one constraint is that you don't use up more of your resources than you have available, right? So, I mean, by the way, everything I'm going to say for the next 20 minutes is really obvious. It's actually really important to say it, though. So, okay. Now, among things that meet the constraints, the question is, what does the objective mean? And here what it basically means is the smaller, the better, right? So it could be something like this, the total cost of a system, right? Or it could be something like the negative profit or the negative utility, right? So you'd want to maximize some utility, maximize a throughput, something like that, an aggregate bit rate. These would be the kinds of things you might do. It might be, the cost might be something like the deviation from a desired or target outcome, right? So how far are you from some desired target outcome? It could be fuel use. It could be the total power. It could be risk in finance, right? So you could set it up in such a way that you'd say, I want an expected return of this, and among all things that achieve that, I want you to minimize the risk. Okay, so this is the simple and obvious idea of what optimization is. You choose these variables, and then you carry them out. This is really the same thing. Engineering design is sort of the same thing. It's on a different time scale, though. So what this is here, this vector you choose, it represents a design. So it's of a device or a structure. It could be the steel frame in this building, okay? And you might be doing things like deciding on the cross-sectional areas of the beams in the building, right? So this is actually almost universally done now, okay? So you would, you would actually optimize over the cross-sectional areas to make sure that it can do things like, support the loads, stay up in certain earthquakes, and all that kind of stuff. Okay, here, the constraints, they can come from the manufacturing process. If you're designing a circuit, there's just certain things you can manufacture with a given process, and you can't violate that. And performance requirements. You're making a circuit, it's got a clock at whatever it is, 2.8 gigahertz, period, right? Or it's got to dissipate less than 130 watts, period. And often the objective is a combination of things like cost, weight, and power. Right? So this is engineer. So this is actually exactly like making good choices, except that in the case of making good choices, you might be making that choice for 20 milliseconds or for the day or something. And here you're committing to it for a couple of years or whatever the life of this thing is. You're going to design stuff. Okay. Here's one that's actually quite different. So it's also, optimization is basically used throughout statistics and machine learning. And in fact, anywhere where people fit data. And it actually is a very different thing here. In this case, these parameters that you have to choose, they are not actions. They're not things you do or cause to be done or transmit. What they are is they're parameters in a model. Okay, so they're parameters in a model, and then what happens is your constraints will impose requirements on the model parameters, right? So if the model parameters are sources of some emissions, they have to be non-negative. If part of the parameters represent a covariance of something, it's got to be positive semi-definite, right? So these are constraints. And the objective is usually, it's got one thing always and sometimes another. So what it always has is it's something like this. It gives you the error of your model on some observed data. That's one case, right? And then often there's a second term, which penalizes model complexity. And this is what allows you to generalize, right? Because in fact, what you don't want to do is fit too well the data you've observed, because you won't fit tomorrow's data that well, okay? So the point here is that in this instance, the parameters are not they're not things you do, like trades or something like that. They're actually just parameters in a statistical model. And essentially all of machine learning and statistics, I mean, we'll see that it doesn't say much, but in fact, you can put it into this this framework. So, okay. Whole other fields, things like, a lot of geophysics, and especially they use terms like inversion, right? And the idea is here, X is something, often physical, that you want to reconstruct or guess, right? So, and the idea is you have a measurement Y. So, I mean, in geophysics, X would be, the details of, let's say, the density of what's below you, and then Y would be measurements you got from magnetic anomalies, right, or gravitational anomalies, or you set off some high explosives and read in the measurements, that's Y, and then so you have some measurements, and then what you want to do is I think people refer to inverting the model. I actually think that's exceedingly bad language, because you're not inverting anything. And it kind of hints back at like inverting a matrix, which is the most naive and also I might add useless method possible for this, right? Okay. So here, your constraints, they might come from prior knowledge about X. You would say, well, the range of densities is between this and this, so I don't want to guess anything that's outside that. Nothing has negative density if I'm actually looking at density, right? So, and the objective might measure something like a deviation between the predicted and actual measurements, right? So these would be the ideas. Okay, so yet another area is actually very interesting. It was given a great name by Stephen Johnson at MIT. It's worst case analysis, right? So here, the variables or actions, what they are the variables, the X, they represent actions or parameters that are out of our control, okay? So the constraints give you the range of these things you're willing to assert. Like, I don't know what the crosswind is going to be when I'm landing, but I'm going to assume it's less than 20 meters per second or something, right? That's something you might assume. And then what you would do is you'd minimize minus f0 of x. That's maximizing f0 of x, which if f0 is something you want to minimize, this is finding the worst possible thing, right? So this is worst case analysis, right? And so the idea is here, I mean, if someone walks up and says, what are you doing? You say, I'm finding the worst thing that can happen, which is, in fact, if you think about it, it's kind of a pessimistic thing to do. I mean, right? And then, but the idea is very simple. If you can actually find the worst thing that happens and it's not too bad, then you can actually have high confidence, reasonably high confidence in this. Oh, and by the way, things built like that and designed like that historically have worked really well, okay? So adding robustness into something is, it's the key in lots of fields. So everyone I know about, that's the key. So this is the idea. So, and here, they're not, the variables could be actions, but they're not actions under our control. They're action under, and in this case, if you actually optimize, maximize f0, they're actually the actions of an adversary, is what they are, right? So, and so I guess in all of these examples, they're not that different, except the meaning of what the variables are and the objective and the constraints are different. These are different use cases. And the last one I want to talk about is optimization-based models. So the idea, it's a very general idea, and it's very old, very widely used. The idea is that you're going to model an entity as taking actions that solve an optimization problem, right? So for example, in economics, you would say, well, an individual or an agent is going to make choices that maximize expected utility. Okay, so this is it's a very common model, right? By the way, you ask someone, what are you doing? Are you maximizing utility? They say, no, I'm buying a car. I'm not maximizing expected utility, right? But I'll get to that in a minute. In biology now, it's a big deal. You'd say that, well, what an organism is actually doing is it's maximizing its reproductive success, or the reaction rates in a cell maximize cell growth, right? It's actually these are very interesting things. Here's one from the 19th century. Currents in an electric circuit minimize total power. So that's from Maxwell, okay? Actually, this is the only one that's actually a good model. It's actually a flawless model because it's a variational principle from physics, so it's actually just true. The rest are, of course, completely wrong. The reaction rates in a cell, they don't adjust themselves to maximize, cell growth. What's happening inside a cell is called biology. That's what happens, right? But it turns out if you make this unbelievably crude model, if you basically anthropomorphize the reaction rates and say they're going to do whatever they do to maximize growth, you get stunningly good models. I mean, just better than they should be. And the same is true up here. here. Now, if you believe it, that's what economists do. That's a big mistake, right? But if you're someone else, like doing modern advertising or something like that, where of course you don't believe your logistic model of whether someone's going to click on an ad. What you care about is how many people click on the ad. And if you have a good model that actually allows you to predict that and optimize it, good for you. And you don't sit around at night thinking, do people really form a linear function and then take the logistic of it and then flip a coin and then, anyway, okay. So actually these are, these are like really crude models. And yet, what history shows is that these have worked way better than they should have, right? Not for any given one person, but I take 10 of you and try to figure out what you're going to click on. If I display something in front of you or what you're going to do, in fact, it's almost embarrassing to find out how well you do with very crude models very quickly. Crude models based on optimization of something, right? By the way, a very interesting question is to observe behavior and figure out what it is they're optimizing. They don't know they're not optimizing. They're flying a helicopter or something like this, but then you can actually impute what they're doing, and then you get a very good model. So, okay, all right. So the summary is you have optimization everywhere. It's just everywhere, right? It's used in modeling. It's used in worst case, now all sorts of things, right? So that's fantastic. That's great. And now the bad news. You can't solve them. So sorry about that. So, it's just but people don't say this explicitly when they teach this. They drag it out over a long time, and it's over several lectures, and you'd have to assemble it all together to realize this is what they're saying, right? Because it doesn't look good. Anyway, okay. So there's an exception, and the exception is convex optimization problems. These are tractable, right? So we're going to get to what that is in a minute, but these are the tractable ones, right? And by the way, this is less bad than you think, right? There are heuristics that will sort of, optimize something, meaning they really won't, but they'll get you something which is maybe feasible or approximately feasible, and at the same time will actually maybe get you a low value of the objective, if not the lowest. And it turns out for many applications, this is just fine, right? So if you're at a hedge fund and it's doing well, you're not going to worry at night that you haven't found the global minimum. But what you are going to worry about is things like, is the model changing and blah, blah, this kind of thing. That's the thing you're going to worry about. Okay. All right. So that's the overview of optimization, and now we're going to talk about convex optimization. Well, it's just a subclass of optimization problems, and it's got there's a couple of requirements, actually just a few. The first is that the equality constraints have to be linear, period. Okay, so that's constraint number one. Constraint number two is that the constraint functions here have to be convex. So this function, which is the constraint function, has to curve upward. So they have to look like this, right? That's it. By the way, they can be flat like that. That's on the boundary, right? And the objective also has to have the same form. So that's it. That's what a convex optimization problem is. Why would you study this? Well, first of all, the mathematics is actually beautiful. So it's just as pretty as information theory. So you'd want to study just for aesthetic reasons. Actually, there's very close connections to information theory. I'm not going to talk about a lot of that because actually I'm going to skip in what you're going to hear today those topics. Those involve duality and things like that. But that's actually it's very close to a lot of stuff in information theory. So you get duality, optimality, it's quite pretty as mathematics. But I think also, more interesting for me, this is a very subjective list, right? But is actually what's really cool is that you have methods that work, and they work in theory and practice, right? So you can you can talk about things like, this is polynomial complexity or something like that, and you get the global solution. You actually get the best point, or a best point, I should say. That's the contract. Actually, what's very important about this is that this makes it go from very beautiful mathematics to actionable. So when you are fiddling around with a problem and you put it into convex form, it's not just a pretty mathematical result. It's in almost all cases, it's fully actionable, meaning you can actually do that. You can implement this. You can do all sorts of stuff with it, and so on. So, okay. One nice thing is you get a conceptual unification of many methods. So, I kind of watched this happen at Stanford, and now, like the first 8 weeks of machine learning at Stanford, and you hear about all these weird different methods. You hear about regression and lasso and logistic regression and multi-class, blah blah. It goes on and on. Each one they would have their own little algorithm for solving and blah blah. What's very nice is actually to be able to say these are actually all instances of the same thing, right? So that's actually just intellectually it just cleans up a lot of stuff. So that's cool. And there's lots of applications. I think this is what's kind of cool. So where are the applications? Well, we've already seen, and you can even understand now how. Machine learning and statistics, I mean, you're basically forming models. And so the models have parameters in them, and these are optimized, like period, right? In finance, this comes up throughout finance. Either, first of all, finding a model. That's a critical part, is finding a model. The next is actually the action. So if you actually run a hedge fund and you want to figure out what trades to make and you want to take into account risk and return and transaction costs and all sorts of other stuff, then that's going to be through optimization. In areas like supply chain, revenue management, advertising, they're all moving from intuitive things to things based on optimization. Control is filled with it. Signal and image processing is moving this way, right? So signal processing, used to be in the 60s and 70s, transfer functions and, so many dB this and that, and here's a frequency response plot in my equalizer. And it's now moved, a lot of it, especially for the non-real-time stuff, has actually moved to things based on convex optimization. So networking, operation of a network, certainly the design, circuit design, combinatorial optimization, the effective methods for this, for bounding, would be through convex optimization. Lots of other areas. Flux space analysis is an area in biology where, I mean, it's just what I said before. You imagine that a cell maximizes its growth rate over the available reaction rates, and it gives experimental predictions gives predictions that are verified experimentally way more than it has any right to. I mean, it's too simple a model. Okay, so here's the approach. The high-level approach is you're going to take you're going to try to formulate your optimization problem as convex. That's what you're going to do. Okay. Now, if you succeed, you can usually solve it numerically. And let me just say that the whole point if this is numerical. It's not about getting a bound, or we're not interested in at the end of the story being, square root n log n. Okay, this is not what it means. Is we're interested in actually doing these things, right? So, and that means so we're not interested in sort of 19th century paper and pencil bounds and things like this. Not that anyone in information theory would ever do something like that, or limits as n goes to infinity. So, no, it's not that kind of stuff. It's more like we're actually going to do this. Okay. And the idea is, you'd solve it if your problem is not too big, and you're lucky, or you just use generic software. Otherwise, you develop your own software. And there's some tricks here. And this is what you'd learn at, if I teach a 10-week course on this, and other people do too. It's taught here. And you'd learn things about change of variables. Then you'd approximate the objective and constraints. Or you do something that has a very fancy name, relaxation. So it sounds very fancy. What it means is you're simply ignoring the constraints that you can't handle. So, by the way, for these approximation methods, I can tell you something else historically that is the case. It's actually extremely interesting. If someone came along to me and said, optimize the fuel use in some vehicle. And then I said, well, tell me about the fuel use. And it was fantastically complicated. There's all sorts of thermodynamics and chemistry. And I didn't understand any, right? And they give me, and we look at it. And we approximate it with something that's convex, and it's, it's within 5%. Well, sure, anyone could expect that this would work well. I mean, right? This makes total sense. But there are a lot of cases where the approximation is like a joke. You actually do a really terrible job of a shockingly bad job of approximation, and the result is actually superb. So this is something I don't think a lot of people know about, or what, It's actually the dirty secret of all this. Okay. So I'm going to say a little bit now about solvers and modeling languages, right? Because this is something that's kind of from the last 10 years, and it actually changes things on the ground. So, okay. So how do you solve one of these problems? Well, if you've got thousands, 10,000, maybe 100,000 variables, then you can solve these by standard methods on a single machine, right? And especially for problems put into a standard form. We're going to talk about that later. Now, these would exploit problem sparsity. And this is not quite a technology, but it's getting there. Right? Technology just means it kind of like always works. It also means, by the way, that whatever it is can be encapsulated and used by people who are not experts in that area, right? So, which is, I mean, a lot of people actually they think this is insulting when you say a technology. It's actually the opposite. It's the highest possible praise, because it means that area, that topic, has been, they understood deeply all of the theory of it. They've worked that all out. They've developed algorithms that they know work and have analyzed, and then they have perfect implementations of them, typically open source, because there's no other way to know that it actually works. So that's actually how, and the result is they expose to the rest of us a thin layer with flawlessly specified semantics that the rest of us can use, okay? And so I get people come and yell at me about this, and I'd say something like, well, do you use like TCP/IP or something? These are people in numerical optimization, and some don't even know what it is, some do, and I'd say, you use it all the time. Do you know how it works? Of course they don't know how. I mean, some do, all right, but most have no idea how it works, right? And I'd say to them, look, that is not trivial. Number one, the implementation. So you're lucky because somebody has figured out this stuff, abstracted everything away, worked out how it works, and you have flawless, perfect implementations. And the result is somebody like you just makes a connection to a socket and everything's going to work out, right? So anyway, okay. So it's used in a lot of areas, these areas, I mean, all the time. So let me talk about large-scale problems. So large-scale problems, these might be in the 100,000 to a billion variables, and of course there are bigger ones, right? So, and these are solved using custom, and they're often problem-specific methods, right? So these would be things like, this doesn't matter, but things like limited memory, BFGS, and stochastic subgradient, block coordinate descent. And so these things, like actually, not quite seriously, while I have been speaking, at least 2 or 3 articles on each of these has appeared in some like machine learning or other area, journal, right? So, and that's fine, right? So it's not hurting anybody really. So these require like a custom implementation and tuning, right? But if what you're tuning is like the click-through model, the algorithm that makes the click-through model at, let's say, for example, Google, right? So, and this is in your critical path of this fire hose of cash coming into your company. Yeah, then it's absolutely worth making a custom implementation. So, of course. And these things come up in large-scale machine learning. Image processing is like a no-brainer. An image already, it's 1K by 1K. You got a million variables right there. So, you're in that range. And there, what it is that people who do image processing typically they make their own. Right? They write stuff in C++ or whatever and so on. It's quite little. I mean, because you can't, the generic things don't yet work for that. Okay. Now let me say a little bit about modeling languages. So the idea is you have a high-level language that supports doing this optimization, right? And so you'll describe the problem in a high-level language, and then that'll be automatically transformed to some standard form. And then you'll have a standard solver that will solve that. And transform the answer back, right? So there's implementations of these things in YALMIP was the first one. CVX, maybe a bunch of you have used. CVX-Pi, in Python, and something in Julia. Oh, and now I get to start one of my rants. So actually, later this evening, someone's going to talk about Python. So which is, anyway, so that's great. I'm extremely happy about that. That's good because, I don't know, maybe some of you use MATLAB? Maybe? Okay, I'll take that to be I mean, I do too. So the first thing is to admit it. It's okay. It's totally okay. So see? So it's okay. It's like a support group. It's okay. Actually, it's not okay. So, but the first thing is to admit it, that you have a problem, and then to move on. So Anyway, so some of you may not know, if you don't travel in wide enough circles, right, you may not know that basically MATLAB is not a language. I mean, it's not, by anybody who knows anything about languages, like anybody in computer science, is not considered a language, right? A language is something with a flawlessly specified semantics, a perfectly specified syntax, right? They must be open source because there's no other thing. There's no other such thing. It's ridiculous to have, you know, to have a call and you'd say, what happens when you make that call? Sorry, wish we could tell you. I mean, it's ridiculous, right? So these are real languages, right? Real languages are things like things you've heard of, you know, C, C++, you know, Java. But Python, these are relatively low level. Python is kind of the standard now is a standard now for higher level stuff. It's quasi-scripting, but actually is quite sophisticated. And Julia, this is just if you want to be really cool. So all of you should just go type in Julia, and then it's a new language coming out of MIT from a year ago, and it's super cool, and it's actually targeted right at the MATLAB users. So if you have friends who use MATLAB and you want to, yeah, because by the way, that reflects on you if your friends use MATLAB, and not well. So that's the reason you would want to get your friends to not, the first thing is to get them to not do MATLAB in public. That's the first thing. And then after that you transition to them not doing it at all. But anyway, but it's a process, and I know. So, okay. So, and there are implementations of these things, and we'll see some of it later. We'll see little snippets. So, okay. So CVX, this is developed, I mean, this is like 10 years old. I mean, it didn't really work 10 years ago, but it did, I mean, it got to work pretty quickly. And the idea is you'd write something like this. What it is it's actually, I mean, it's just readable, right? So basically you write down what you want. It's actually very interesting. In computer science, you'd refer to this as a declarative style language. Instead of a procedural. Procedural says, do this, then do that, then do this, then do that. Oh, if this happens, do this, otherwise do that. That's declarative. That's procedural, right? I mean, anyone in computer science will be rolling. I mean, that's hideously oversimplified. Declarative, you just simply say what you want. But that's what optimization is. You say, you're not saying how to get X. You're saying, find me an X that satisfies, these are the things that are non-negotiable, and then this is the thing. If there's anything left, any degrees of freedom left over, this is what I'd like you to do with the extra degrees of freedom. Okay, so that's declarative in style, right? So, okay, so this is just like highly readable, and then the idea is this would be converted into one of these standard forms and solved, right? So, by the way, that standard form is very interesting. It's essentially something like it's intermediate code for optimization. I think that's actually the right way to think of it, right? So that you write in a high-level thing, this gets compiled or transformed into this low-level thing that basically no one should look at except for the very few people who work on, building the virtual machine that handles those things. And this is the analogy is actually flawless here, right? That it works perfectly. You need a few weird people to work on those small things so that the rest of us don't have to worry about it, right? So that's the idea. Okay. CVX-Pi is it's a Python version, and it's actually very interesting. So actually, how many people here use Python? Oh, that's good. That's good. Okay, so these are the cool people. Everyone else, those were the cool people. I'm just saying. Okay, I'm not kidding either, by the way. So yeah. So could you hang out with them actually, and would you please get them to use Python? Thanks. Okay, fine. So it's a different, I mean, it's a good thing because once you start learning about it, you start thinking this way, and it's actually a very good way to think. So this is what it would look like. Here, variables live outside of optimization problems. They're just free-floating, they're objects and classes, they just sit there. And so this says, you form a variable, that's a constructor for a variable. You form cost, that's an expression here, so that's an object. Abstract object. And then prob, this actually forms an optimization problem. From minimize cost, cost is an expression, minimize of cost is a function that takes an expression, and what it returns is an objective, something of type objective, right? This is the constructor for making a problem, and it says make a problem with this objective, and this is a list of constraints. It's a list, however, with just one entry, right? Which is that the infinity norm or whatever should be less than 1, okay? And then what you do, this constructs the problem. It's an object now. And then you call the solve method on it. And what that will do is that will actually overwrite, it'll actually go into the variables, and it will actually assign the value field and attribute. Okay, so this is the idea. So, okay, so, and when you all learn Python, this will look very natural to you. Okay, so in Julia, just to show you, there's a new one. This is relatively new. Oh, by the way, this was implemented by a sophomore in computer science at Stanford. So not a random one, obviously, because it's someone who took PhD level courses in optimization and math. But you know, the point is, this does not require it just requires the right combination of things. But in CS, we're talking undergraduate topics. These are all undergrads, except for Madeline Udell, who is my PhD student who just finished. These are all undergrads. Yeah, they were all undergrads. Not me, I guess, but so it's same thing. I mean, so this is in Julia, and I think it's all pretty obvious. The only thing you wouldn't know here is that this exclamation point tells you that this function here has a side effect, and the side effect is that it's actually going to write the value attribute on X, right? And so, actually, how many people have seen or heard of Julia? A couple. Oh, that's good. Okay. So, by the way, that's even cooler than not. I mean, it's yeah, it's getting there. It's pretty cool because then you're on the bleeding edge. I mean, there are other ones that are also weird, like you could know Lua or something, or Haskell or Scala, but for ones that are kind of even credible, Julia would be a good one. Actually, the rest of you just spend some quality time on the web finding out what it is. Just drop that casually the next time you're with a group of people and see what happens. And just because anyway, trust me, your social status is definitely going to go up. So if you handle it correctly. So, okay. So you have modeling languages. So, what this does is it enables you to do rapid prototyping for small and medium scale problems, right? That's ideal for teaching. It's great because, I mean, I know this because I taught a class on this before we had these modeling languages after. And before, we do a lot of math and everything. And look, of course, this stuff is useful. You know that. But then, it was kind of a pain in the ass to actually make the students do this. And they'd spend a lot of time coding something, and then they'd see something. And it actually even sent the message that doing this is kind of a pain in the ass. That was actually the message that came out, right? Whereas, in fact, what's nice is nowadays, it's a 15-line script at most. I mean, you can do like extremely sophisticated signal processing, image processing, finance, machine learning, statistics. It goes on and on. Control. In like 15 lines, you can do this. And so the coding time is like approximately 0, right? So so actually, for teaching, it's changed a lot. And so I won't say anything more about this and just move on. And now we're just going to finish up this section by just looking at some examples. And so the first we're going to look at, these are more details, right? So now we're going to look at one. The first one is radiation treatment planning. So here the idea is you have somebody with a tumor where even the surgeons are who are not known for humility say that might be beyond me or something, but I know because I have friends who do this. And then you have a tumor that's like very near something that is very tricky or something like that. And so the idea is you actually send in beams. It depends on what kind of machine it is, but some high energy beams into a patient. And you have various beams. You can choose the intensity of each beam. It's actually done by a machine that moves this thing around, like a linear accelerator. And then it's got lead sheaths that come and block or open the opening, and then that controls the beams, right? So that's actually how it works. And then you divide up the place that you're irradiating, like a head, and you divide it up into voxels, and a typical number would be 1 million. I mean, that's, 1 million, 10 million, something like that, right? So that'd be like 100 by 100 by 100 vox region, right? Now the mapping from the beam intensities to the radiation doses is linear. So you just write as y equals ax, right? Now the entries here, they're all non-negative, but they come from beam geometry and physics, right? So it's actually very complicated. That's a whole subfield is producing A. And part of it would have to do with things like, beams get attenuated as they travel through different structures. They scatter, they hit bone and they scatter a little bit, and there's all sorts of stuff there. But the point is, for the rest of us, this is y equals ax. Okay? And the goal is to choose x. It's got to be non-negative. And the idea is you want to deliver. You would like yi, the received dosage in voxel I. You'd like it to be something which is the prescription, right? So obviously it's 0 for non-tumor cells, right? If there's something that's not a tumor cell, you don't want to irradiate it at all, right? For the tumor cells, this thing is positive, meaning you really want to put a certain minimum amount of radiation on it to kill or damage those cells. So this is the goal. Okay. Now, the fact is there is no x that's non-negative and satisfies y equals d. That, by the way, that would be that'd be perfect, right? There'd be some very clever thing that would put 0 radiation on any non-tumor voxel and would put exactly the prescribed dose on it. There's no such thing. For one thing, the radiation has to get through the person to get to the tumor, right? We can start with that. But that's silly. Okay. And if you want to know what a typical problem looked like, it might be 1,000 beams and 1,000,000 voxels. That would be a typical problem. Okay. So here it is if you write it out via convex optimization. It's fairly simple. It looks like this. What you're going to do is you have your variable is going to be x, and we're going to make y a variable too, right? But they're constrained by physics. So this says that physics has to hold, right? So we'd say, and then what we care about is that we're going to minimize an objective, and our objective is going to be this. If you take yi minus di, that's how much you overdosed. If that's positive, that's how much you overdosed that voxel. Okay? And then, so the plus part is we take that if it's positive, otherwise we take 0, right? And so this is literally how much you have overdosed the voxels. Hopefully for many of them it's 0 or something, right? And then we multiply by a positive thing which weights the badness of that. Di minus yi, that's supposed to be a minus. That's a typo. Okay, if this should be a minus. Oh, no, sorry, it's correct. I switched di and yi and confused myself. Okay, sorry. Di minus yi, that's the dosage minus delivered. If that is positive, it means you, yes, then it means you underdosed. Okay? So, and here we charge for underdosing too. Right? And so these are weights, and the radiation oncologist would fiddle with the weights to get what they want. Right? So that's the idea. Okay. That's a convex optimization problem. Okay? So, so here's an example. This is a real one. Actually, I think it's someone from San Diego. So here it is. It's a case with 360 beams and 360,000 voxels. It's actually a relatively small problem. And then I think this is, actually you couldn't visually see the difference between the actual plan that was used and the one found by this method, just by solving this problem. They were actually identical or like within, I guess they'd say they were therapeutically equivalent, right? So a radiation oncologist would look at both and say, okay. But that actually was kind of interesting. This just came out in a few seconds on a GPU. It's a small problem, right? And the original plan, I think, took 8 hours of least squares weight tweaking, right? That's where you say, oh, there's too much on the thyroid. I'm going to crank these weights down, and then I'll push these weights up and stuff like that. Okay, so this is an example of a real thing. This is extremely current. It's being used and stuff like that. Okay. And that's an example, by the way, this is a perfect example where the variables represent actions. Because when you choose one, if you have x37 is the amount of beam 37, and that means this giant thing moves a linear accelerator, some lead sheaths open to a specified amount, and a linear accelerator turns on and aimed at someone's head. Okay? So that's a case where for sure the variables were actions. Desperate ones, but they were actions. Okay. In the next one, this is going to be an example where we're inverting something. It's like an inverse problem. So here it is. What we have is you have an image, and a bunch of the pixels are either obscured or corrupted, and your job is to fill them in, right? So, and it should be in such a way that it's visually, that it looks plausible, right? So total variation in painting, this is now coming on 2 decades old. It simply says you should do the following. You should pick the unknown, the pixel values to minimize the total variation. And the total variation is this. This is the value. X is it's a 3 vector. It's RGB. It's the red, green and blue, whatever color representation. And it says this is the one to the right. And this is the neighbor to the right. So this is sort of like the derivative. It's the derivative in this direction. And this is the derivative in this direction. And so you stack them together and you get a vector. And then you want to minimize the norm of the whole thing. Right. By the way, you minimize. It's extremely important that this does not have a square here. If I put a square, if I minimize the sum of the squares, then I'm back to 19th century. That's the Laplacian. That's the Laplacian. And that's what we call Laplacian smoothing and stuff like that. And actually, it wouldn't look anywhere near as good. Right. So this is actually, it's very critical that this should not be squared here. But the point is that's a convex problem. Okay. So here's an example. It's Lena. If you know image processing, you know about Lena. So here's the original image, and then we simply corrupt it like this. So I think we're removing like 20% of the, maybe 10% of the pixels are just removed, right? And so your job is to fill in. By the way, these are more than 1 pixel thick. I mean, these are wide. It's 512 by 512 image. So your job is to fill stuff in. Now, obviously, what they should look like, they should be the color of sort of the surrounding areas, right? I mean, that's clear that they should be. Ooh, I think this just failed. No, there, okay. So, I mean, so you can easily make something where you looked around at known pixels and kind of made it look like those, made it an average of those. Something would happen. Actually, what would happen would not be as good as what happens when you minimize total variation. So to minimize total variation, you write a 1-line, 2-line script in MATLAB or whatever, in Python or Julia, and this is what happens. Okay, so actually, how many people? So for the first thing, okay. By the way, if you're not shocked, you should be. If you're not shocked, then you do not understand what just happened. Okay. So basically, I guarantee from where you're sitting, you cannot see. You can't see that. I mean, it looks like it's done perfectly, right? This is very hard to do because there's things like edges, right? If you have edges here and you do ordinary smoothing, you're going to see any other method of infilling, and you're going to see all sorts of artifacts from the edges, right? So this none. By the way, you can do better than this by using a more sophisticated objective, right? But the point is, this just shows you with using like a super dumb, super simple, but convex objective. This is from the 90s, right? You just plug it in, and this is what happens, right? So, okay, I hope people are impressed, right? Because this was, oh, by the way, you can take the difference of this image and it's not 0. I mean, duh, it's not like it's clairvoyant and figures out what the missing values was. What it is filled in such a way that, I guess it's a psychological and perceptual fact, it looks just fine. Everybody, right? So the point is that perceptually, it did a really good job, even if it guessed the wrong values of the pixels, right? You can even zoom in and it does crazy things where it actually continues correctly the edge of the hat, just because, well, I mean, it's solving this convex problem. Okay, everybody got this? So, okay. Just to see like how far you can push this, let's just remove 80% of the pixels. Okay? So we're just going to keep 20% and fill it in. Again, the same 3-line script. And that's what you get. It's not perfect. I mean, that would be too weird if it was perfect, right? I mean, that would be actually like positively weird. It's not perfect, okay? But it's actually like weirdly shocking. How many people have seen this or taken a class on image processing or? Okay, well, that's good. Did you see this actually? Like total variation stuff? No one's answering. Is that, don't worry, I'm not gonna inquire about your MATLAB use. Okay, so did you see total variation stuff in your class? You have to understand I can't actually see anyone because the lights are in my face, so I have to kind of guess. Okay. There we go. Okay, there we go. So, no, you didn't see this. Okay, was it? So it's probably kind of a boring class, is it? Or how was it? But we're going to fuzz your head out, don't worry, so no one, the professor is not going to be able to find out later. Don't worry. And we're going to change your voice too, so, okay.
Okay, I won't tell you which.
Okay, fine, fine, okay, so, all right, good, all right. So, okay, that's that. Okay, next thing we're going to talk about, just a quick example, is in control. So in control, you have a system state that's xt or something like that, and then you have a linear recursion that tells you how the states recurse. And then you'd have constraints that the inputs, that's these things, these are the actions you're going to take, and a state, and that being a constraint set, and you might have a terminal constraint. And you're to minimize this so-called stage cost plus a terminal cost, right? So this sort of abstract problem, by the way, comes up like everywhere. So it's things like vehicle control, it's engine control, it's things like flight management system. It's everything, right? And it goes to a lot of other stuff as well, right? So, okay. So this is the idea. When these constraints are convex and these functions are, this is a convex problem, right? So here's just a quick example where you have something with like 8 states and 2 inputs and horizon 50. You just take a generic system. We limit the input to have an infinity norm less than 1. And then the idea is we need the final state to be 0. That's called a regulator, because usually x equals 0 means you're back where you wanted to be, right? You have some place where you're cruising at whatever it is, 33,000 feet at Mach 0.81, and that's x equals 0, and then this will get you back there, right? So, by the way, there's a lot of control theory, I know, because I taught a lot of it and stuff like that. Most of it, by the way, for this is totally and completely useless, so I don't mind saying. It is. It's just the classical stuff won't handle things like this. These are fully real. It will handle this, right? That's the traditional objective. And you get something like this, like that, and it's, these things are just not obvious, right? This is with like 2 inputs and 8 states, and it basically says, the first thing should be at 1, then go down to -1, then up to 1, and who knows, right? The point about this is it's not remotely obvious. You're way beyond what any human being could do. Way beyond, right? Even, by the way, a super good pilot, right? There's just no way. Okay. We'll look at another one. This one is from Statistics and Machine Learning. So this one is, the idea is this. You're given data. Data consists of a pair of things. The second thing is a Boolean label or outcome. So it's +1 or -1. For example, it might be that loan turned out to be, that financial transaction was fraudulent, or that it's not. Or it could be that email was spam, or it's not. Something like that. Or it could be that user clicked on that ad or not, right? So these would be the kinds of things the data would look like. And then associated with this plus minus, this Boolean thing, you actually have, these are big. You get a big vector xi, and what it's filled with is all sorts of stuff it's filled with all sorts of things about it. These are features or attributes, regressors, whatever you want to call them. And they might be things like this. If it is a financial transaction, it would tell you, it would obviously have, the amount. But it might have other things associated with, like, where is the purchase being made? What's the category? What's this? What's that? Well, how much has the user charged in the last week? How much in the last month? This kind of, to have a long string of things. If it's email, this could include things like the counts of various words. So it'd be word counts in the email. There'd be one feature that says, is this email coming from, let's say, Romania? Right? That's a single feature. It's either 0 or 1. And so there'd be a lot of these. And the idea now is that you are going to make a predictor. And your predictor is going to be this. You're just going to make your variable is beta and v. This is a vector. And you're just going to add up all the weights of these features. You're going to add them all up. And then what you're going to do is subtract this offset and then take the sign. If it's positive, you're going to guess it's a +1. It's spam. If it's negative, you're going to say it's not. Okay? So, and the question, of course, is, well, how do you find these parameters, right? And an answer. Actually, there are multiple answers. By the way, most of the answers are basically convex optimization. I mean, there's more sophisticated things now, but the simplest ones are things like this. It says that you should minimize this function here. And it makes total sense. You actually want this to have the same sign as that. That means you correctly identified that example, right? Whenever this is +1 and that's +1, you did good. If that's -1 and -1, that's good. So you want these two to have the same sign, okay? But in fact, what you're going to do is, this is homogeneous here, so it's not just that you want it to have the right sign, you want it to have a margin, which is why this is called support vector machine or something. Anyway, yeah, so you want a margin, and that says I really want this to be, not just to be positive, but to be more than 1. And what this says is, if you're more than 1, I'll charge you 0 on that example. If you're less than 1, I'm going to charge you linearly. By the way, if you're less than, if this thing is less than, if this is less than 1, I'm going to charge you. By the way, if it's less than 0, it means you actually made the wrong guess. Okay? So I won't go into the details of this, but it's completely intuitive. It makes perfect sense. This is some horrible function. Because when you have the plus part, that's something that's 0, and then when something's positive, it goes up, and it's got a kink right there. And so in the sort of the classical optimization course, this would be a Western optimization course, I might add. This would be a disaster because it's not differentiable, right? And the whole course, starts by talking about gradients, then droning on about, gradient method, quasi-gradient, conjugate gradient, Newton. It goes on. How many people have had that course? Okay, fine. Good. I'm glad. So anyway, okay. All right. So the point is it's a convex problem and you solve it. This second term says, I want you to minimize the sum of the absolute values of the betas, and that's actually something, this is a big deal right now. It's called a sparsifying regularizer, and it actually tends to find a beta that's sparse. Sparse is super interesting, because if an entry of beta is 0, it says it's ignoring that xi. So that says that I might, these would be very typical numbers, like for email, I might have 1 million raw features, right? Including that one I mentioned before. One of the features is, did that email come from Bulgaria, let's say, right? Or Romania, right? Then it's what this will do is maybe that beta, the corresponding beta might be 0. And that means, thanks for offering the use of that regressor, but we're not going to use it, okay? So this is also very widely used in medicine, right? So in genetic things, you have 30,000 gene expression levels. You want to fit a model, and you say, thank you for offering me 30,000, the levels of 30,000 gene expressions. I'm only going to use 52 of them, okay? So that would be a typical model, the way that works. Okay. By the way, we are at the forefront now of sort of, this is current research in all of these areas and applications. Right? How many people have seen this kind of stuff in a machine learning class? Okay, that's not enough. If you didn't raise your hand, please go take one of these classes. Sorry, but you might even want to do that while you're learning Python. So we'll convert you to cool. You'll see. But no, trust me, you should do this. You really should do this. Okay. So if we do this, here's an example with like 20 features, and you train and you test them on 1,000 examples each. And this tells you what your error is as you increase this parameter, lambda here. And you're not doing so bad. You're making 15% errors. And then if you tune that up, you get down to, you approximately have it. You get down to 8 or 9% errors. Okay? So, by the way, one of these curves is testing on the data that you were given. The other is actually your performance on data you've never seen. And the fact that these two line up means you did what you really wanted to do, which was not to solve an optimization problem, but make a classifier. It means you've really made a classifier. Okay? So, I mean, these are like super duper obvious ideas in statistics and machine learning, but still. Okay. Here would be the path. There's only 20 of these, so here they are. And you can see that as lambda increases, what happens is these things extinguish. They go to 0, and then they often will then stay 0. Although there are cases where things go to 0 and then pop up again and stuff like that. So, and I think we figured out that this was a good value. And actually, at that value, I think it's using 1, 2, 3. It's using 4. You offered it 20 features to make a classifier, and it ended up using 4. Okay? So, I mean, not that that's a good thing or bad thing, but I'm just saying this is very typical, except that instead of 20 and 4, it's 20 million and 400, right? But other than that, in which case you can't plot it. So, okay. So I'm going to wrap this portion up right now. So the summary is that these problems arise in a lot of applications. By the way, sometimes exactly, right, like radiation treatment planning, you don't have to do anything. You don't have to change the problem, make any approximations at all. It just is, right? A lot of problems like this work. In other cases, you know, the creativity is in making up a surrogate optimization problem, and the idea is if you solve the surrogate, you'll actually like the results. Inpainting was a perfect example of that, right? The true objective is the real objective is actually something like this. I get a panel of, like, let's say I take some undergrads, right? So, you know, like slave labor. I force them to if they take a class on this, and then they have to rate things and say, oh, that's good, that's bad, that's good. And so the real objective is to make it perceptually work. Like we'd say, we'll show them two images and they'd say which one they think looks better, right? So that would be the real goal. But instead you solve a convex problem and okay, all right. All right, so the point about these problems is you can solve them effectively. If your problem is not huge, you can do this using generic methods. If they are huge, people develop custom methods for huge problems. That's always been done, you know. So it's never been a problem that once someone said, I would like to solve that problem, and it actually works well, people are going to figure out ways to solve it, even if it's huge. And the other point here is that things like high-level language support actually makes the prototyping like really easy, right? That it really was kind of a pain in the ass beforehand to do this, and now, or I guess the right way to say it is, even a professor can do this, which is kind of, actually, I asked the students like if that made them nervous, right? Because it means they may not be needed, right? Because that's the whole point, is you go to the student and you say, hey, write the code to minimize total variation, let's see what it looks, try it on these 50 images and let's see what it looks like, right? But now if you don't even need the grad student, you can just type it yourself. Anyway, weirdly they weren't nervous, I don't know why. But they should have been. I think they should have been. Okay. So, all right. I want to close up this portion of this by saying, you know, it's an overview of a field that's like 100 years old. I mean, most of what I showed you is from the last 10, 15, 20. And it's done not by me, certainly not by me, but it's done by, let's say, me and 200-300 of my friends. Okay, so that would actually be the right number, right? So this is, I've just been showing you stuff from all over, you know, huge areas, right? I mean, this is what Google is for, so you type anything remotely related to this, you're going to find these things. And all of these things are available online. So, okay, so what we're going to do is actually, well, maybe we'll have a couple of minutes for questions now. This was not very technical, but if there are questions now, I'd be happy to answer them. Then we're going to break for 15 minutes. And then we're going to come back. And then we're going to do some math. So, which is weird because that's the worst time in terms of blood sugar of the day. But we're going to do it anyway. So, okay. So if there's questions on this, I'd be happy to answer them. All right, let's, we're going to go ahead and get started. So what we're going to talk about now is, well, it's a combination of the math, but it's actually, the math we're going to focus on is the part that's actually actionable. It's what comes into these systems for these domain-specific languages for optimization. Okay. So I'll just recap quickly what convex optimization is. We'll look at this idea of constructive convex analysis. This will lead us to the idea that you'd have in computer science of disciplined convex programming. Then we'll look in more detail at these modeling frameworks, and then I'll wrap up. Then after that, if we have time, we can look at one or two examples in more detail. But we'll see where we end up. Okay. So the first thing is just a quick, rapid overview. You saw this, you know, an hour and a half ago. But just to remind you, what the standard form is you minimize a convex function subject to some convex inequality constraints and linear equality constraints. So that's a convex optimization problem. And what I'll show you now is what has emerged as essentially the standard intermediate form. It's called a cone program. At first it looks super specific. It looks like this. It says you minimize a linear function, not a convex function. linear is convex, subject to linear equality constraints, and all of the nonlinear constraints and the nonlinearity in the objective has been moved into a single constraint that says that the variable is in a cone. Okay? Now that cone, if this cone is, say, the non-negative orthant, this is a standard linear program. That's something, standard from the 1940s or something like that. Actually, it goes back even earlier. If this cone is something more sophisticated, like an encoding that says that a matrix is positive semi-definite, then you move right to the forefront of research, and this would be a positive semi-definite program. Okay? So, and the point is, this is something like the modern canonical form. There are people developing solvers for exactly this class of problems. I don't know, a couple hundred of them, maybe not even a couple hundred, maybe fewer. And that's the idea. There's commercial ones, there's open source ones, and so on. And the idea is that this is the intermediate form. You take a normal the problem that you want to solve, and you compile it or transform it to this form, and then you'd have a choice of whichever solvers can handle your problem. Okay. So we talked about this last time, but I think I'll just review some of it, right? That you have a beautiful and complete and a useful theory. You have algorithms that will actually solve them, and that makes this actionable. And you have lots of applications in lots of areas. We saw a couple of them. So the question is, how do you solve one? Well, you can use an existing custom solver for your specific problem. So if you do machine learning and you decide, oh, I like this idea of a support vector machine, I'm going to try to use my data to make a classifier, there's no reason to do anything other than go to the Google and type, source code support vector machine, and pretty quickly you'll be there. You'll type make, and you'll have a custom solver just for your problem that'll work really well. So that's sort of the best thing. That's not really research, right? But it's fine. The other option is you can develop a new solver for your problem, and you can use a currently fashionable method. This is good. You can write a paper about it and go to NIPS or whatever, this kind of thing. This requires work, but the nice part about this is if you're lucky and you know what you're doing, your method will scale to very large problems. That's good. Or, here's an alternative. You transform your problem into a cone problem and then use a standard cone solver, right? And that can be done by hand. That's kind of a pain. And it can also be done completely automated using domain-specific languages. And we're going to talk about that. So, and this brings us to constructive convex analysis. So we'll say a little bit about this. So, a function is, that's a convex function. That's a concave function. And that's an affine function. And note, actually, affine means the curvature is 0, right? This means the curvature is non-negative, or in this case, positive. This is like negative curvature, and that's 0. And in fact, an affine function is a function that's both convex and concave. It's right on the boundary. It's 0 curvature, okay? So that concave is negative if it's convex. It's affine if it's convex and concave, and so on. So, okay. Now, how do you verify that a function is convex or concave, right? So verifying affine is easy, right? You check if the function has the form of a linear function plus a constant, and then if it does, it's affine. If it doesn't, otherwise, right? But actually verifying that a function is convex or concave is actually quite a bit harder. And so the approaches are, you just take the basic definition. You go back and you show this, right? You want to show it's concave. You say, well, take an arbitrary x, arbitrary y in the domain, take an arbitrary theta between 0 and 1, and then just argue brute force that inequality holds, right? That's your, that's okay in some cases. You could, if it's differentiable, you could use various rules that use the derivatives. Like, for example, if it's twice differentiable, if the Hessian is everywhere positive semi-definite, the function is convex, period. But really, probably the best way to do this, and again, if you're going to do stuff in practice, is to do this via convex calculus. And what this means is you're going to construct your function using a library of basic functions that are known to be convex or concave. We're going to look at a bunch of these. And you're going to use some calculus rules or transformations that preserve convexity. By the way, the reason the word calculus is being used here is not just because it's actually the correct word in English, but it's actually even, the analogy is historically correct. The whole idea of calculus is a way to mindlessly, calculate derivatives of things, right? And so that's the idea. The idea is you have this something like that. So, and it's the same thing. You'd have compositions and stuff like that. Okay, so, all right. So let's just look at some basic examples, right? And it's going to get very specific now. And these are good things to know. We're going to cover some things that probably some of you don't know. And they're really good things to know. So here they are. Oh, by the way, if you're sitting there thinking, I'm in information theory and I don't need to know this, yeah, maybe you're not going to be writing scripts in Python to solve things, right? Trust me, knowing there's no amount of convex optimization you would be sorry you knew. I mean, actually convex analysis, I should say specifically, right? Even if you're not going to do it, you need to know it. Because half of the inequalities you know about derive immediately from this, right? So, okay. So one would be powers. So, x to the 3/2, for example, when x is non-negative. You just visualize what it looks like. It goes up like that, right? It's convex. 1 over x is convex. That goes down like this, right? X squared is convex, right? These you could just check by, you take the second derivative or something, right? Exponential, that's convex. Negative entropy. So the negative entropy is a convex function. You know what it looks like. It dips down, has infinite derivative. It dips down and goes up again, right? So that's convex. Well, an affine function, right? So a linear function plus a constant. That's, of course, is convex. It has 0 curvature. Its second derivative is 0. Okay? A quadratic form with a positive semi-definite matrix. That's going to be convex. It's because its Hessian is 2 times p, and that's going to be positive semi-definite. Any norm at all, that's convex. That follows from the triangle inequality and homogeneity and just properties of a norm. Here's one, the maximum of the bunch of entries of a vector, right? That's a horribly non-smooth function, right? That when the maximum is repeated, right? If there's a tie for maximum, this function is not differentiable, right? And so that's an example of that's a good example of a convex function. Okay. Here are some basic concave functions. Yeah, I mean, by the way, these are things that just everybody needs to know, period. It doesn't matter what field you're in. If there's math involved, you need to know these things. That's my opinion. So here's one. Powers with p between 0 and 1, these are concave, like square roots. So that just goes up like this. So it's concave. Log, that's concave. Geometric mean is concave. Quadratic form with a negative semi-definite matrix, and the min of a bunch of entries of a vector, that's a concave function. Okay, these are things you should know, and now it's going to start getting interesting. So here are functions that you might not know. Here's one, x squared over y, 2 variables, y is positive. Okay, so that's actually the simplest convex function that most people don't know. It's not obvious, it is not remotely obvious that it's convex, right? I mean, bits and pieces are. If I fix a positive y, it's a positive number times x squared. Well, of course that's convex. If I fix x, it's a positive number times over y. Of course that's convex in y. But this assertion is much stronger. It actually says that it's convex jointly in x and y, right? So these are good to know about because you never know when functions like these are going to come up. And the answer is once you know them, they come up a lot more often than you ever would imagine. So generalizations is the norm squared divided by y. Here's one. X transpose times y inverse x, that's jointly convex in the vector x and the matrix y. Okay? By the way, these things, if you took my class, you know these things. Maybe you forgot them, but you should know them. These are just very good things to know, right? These come up all the time. Here's one, log sum exp. That's also called the softmax in some fields. That's convex. It's a smooth approximation of the maximum function. Actually, this, if you're in communications, that's the dB combining formula, right? It says that if you have a bunch of things adding incoherently, like interferences or something, and you give the interference levels in dBm, this tells you what the sum will be, right? This converts to powers, this adds the powers, that converts back to decibels. Okay? I said that fast, but if you speak that dialect, you know what I was saying. So, okay. Here's one. The sum of the the sum of, let's say, the 4 largest entries of a vector. Okay? It's not obvious. That's convex. Okay? This is not obvious at all. Here's one. It's clearly very closely related to things like KL divergence and, I guess what he calls relative entropy, right? So it's related to those. It says that x log x over y, when x and y are both positive, that function is convex, jointly in x and y. Okay? Here's one. Take a symmetric matrix and take the maximum eigenvalue. That function is going to be convex. These are not obvious things at all. I mean, for example, this one, if you just try to imagine what this is, right? I might add, there's no formula for this, right? If x is 5 by 5 or bigger, there's no formula. Because first you'd have to write out the characteristic polynomial of x, right? Which is a polynomial of, let's make it degree of 5 by 5. You write out a degree 5 polynomial. There is no formula for the roots, the 5 roots of a quintic. There is none, right? So for a quartic, you could write it out. It'd be 2 pages long, right? Some horrible expressions. And then you'd take the 4 roots and you take the maximum of those 4. It'd be some horrible thing. That's a convex function. Okay. Here are some concave functions. These are also less basic. These are things you probably should know. And you probably do know some of these things. One would be log determinant of a positive definite matrix. Okay? It'd be the entropy of a Gaussian with covariance x or something like that, right? Here's one, the determinant of a positive definite matrix to the 1 over n. By the way, that's the matrix analog of geometric mean, right? And that's actually a concave function, right? So, by the way, these are known for 100 years, right? So that they almost predated even the common use of the words convex and concave, right? So, but the fact that these functions satisfy these inequalities, which later became known or was becoming known right about then as Jensen's inequalities, that's the defining inequality, it is interesting, is that people already knew these things. Here's one, the log of the cumulative density function of a Gaussian. Okay, so everybody knows what that looks like. CDF looks like that. And the log of it looks like this. It's like 0 up here where it's about 1, and then it goes down and it's convex. Okay? So these are just not obvious things, right? So there are a lot of other ones that are even less obvious, but this is just to give you some quick examples. Okay. Now what we're going to do is I'm going to tell you about calculus rules and how do you combine things and that kind of stuff. That's the idea. So, and this is how you tell it to a person. I'll show you in a minute how it's going to simplify. But here's the idea. Some of these are like really simple. Here's one. If you have a convex function, then 2 times that convex function is convex. I mean, well, duh. I mean, if it curves upward and then you double it, it curves up, actually twice as much. So, okay, that's obvious. The sum of 2 convex functions is convex. I mean, these are like 2-liners, right? So you can work these out. Affine composition, right? If you have a convex function and you shove in as an argument an affine function, that's going to be convex in the original argument. Again, these are just like 2-line proofs, right? They're very, very simple. It's going to start getting interesting now. How about this? The maximum of m convex functions, pointwise maximum. That is convex. By the way, this is really interesting because unlike these, this one actually it generically creates non-differentiable functions, right? So for example, let's take 2 affine functions. So one like this, one like that. And the maximum is the function that goes like this and then goes like that. And it's got a corner, right? So the maximum of a bunch of convex functions is convex. Then there's a composition rule. It says that a convex increasing function of a convex function is convex. So you'd have, if you have h of f of x, that's convex. And there's similar rules for concave. There's a few more advanced rules, but the truth is these are really mostly the ones you need to know. Okay? Actually, well, let's look at some examples first, and then you'll see something even cooler. So, all right. So now we can actually you just put these together, right? So here's one. A piecewise linear function, you write it as the maximum of a bunch of affine functions, right? So it turns out that's convex. How do we show that? Well, we know that the max function is convex, and you can precompose an affine function with a convex function with an affine function, and that's convex. So that's convex. By the way, that's way better than trying to just prove this by yourself. You'll be in big trouble. It wouldn't be fun. I mean, you could do it, but here's one. L1 regularized here, least squares cost. So ax minus b squared plus lambda x1. This here is a convex function of x, right? And the argument would be the norm squared, or the sum of the squares, is convex. That's an affine function, so that works. Let's see. X norm x1, that's a norm, so it's convex. I multiply by a non-negative number, that's convex. And then I use finally the idea that I add two convex functions and they're convex. And by the way, if you could follow what I'm saying as I go through this, what I'm really doing is I'm making the parse tree of this expression, and I'm going node to node. I'm walking the parse tree and applying the rules. Okay? That's all. That's what I'm doing. I mean, you might not think of it that way, but that's what you're actually doing. Okay. Here's a cool one. The sum of the k largest entry. How do you know that the sum of the 4 largest entries of a vector is convex? Well, the argument would be this. Just imagine in your mind taking a vector x with n elements and take the inner product of that vector with a vector that has 4 ones in 4 different places and zeros otherwise. When you do that, that's a linear function, and it's the sum of 4 specific entries of the original vector. That's linear. Okay, so it's convex. So the maximum of all n choose 4 functions of that form is convex. But the maximum is exactly the sum of the largest 4. Everybody got that? So we just did it with not much pain. And this is something that's quite sophisticated. It's not obvious. Okay. Log barrier. I think I won't go into the details on that, but we'll skip to KL divergence, right? Oh, by the way, this is the KL divergence, which you may not have seen, because you've probably only seen it applied to probability distributions. I guess I'm right on that, right? So this is actually the extension of KL divergence to the entire non-positive orthant, meaning it works for unnormalized distributions. I think those are otherwise known as things that are non-negative, but whatever, right? So, of course, what would happen is the sum over I of this would be 1, and that would be 1, and they would cancel. But this is actually what the function really looks like. You don't normally see these, I think, right? And so what it says is that's actually jointly convex in U and V, which I suppose you knew. Yes? I think these are things people know. Okay. So, okay. Now, here's what's cool. I'm going to show you something even cooler. When you tell human beings about this, you go through these rules, and they're kind of obvious, right? It turns out that there's not, these are like 5 rules. There's not 5 rules. There's one. There's only one. There's a common parent of everything. So it turns out that common parent is really simple. It looks like this. It says, so in fact, it turns out this is the only rule you need to know. It is non-trivial, but once you know it, you know a lot. So here it is. It says that a function with k arguments is convex when the outer function is convex, and for each argument, the following is true. Fi could be affine, in which case that's it. Or this outer function is increasing in that argument, and this thing is convex, or this thing is decreasing, and that's concave. Okay? And there's a similar rule for concave compositions, right? And it turns out this gives you everything. Let me show you. How about this? Here's a silly thing. Let's use this to show that the sum of 2 convex functions is convex. I mean, this is going to be stupid, but here it goes. So my function h is going to be the following. H of uv is u plus v. Everybody got that? That's a linear function, so it's convex. Okay? Also, the function h of uv equals u plus v is increasing in both arguments. Okay? That says, according to this rule, it will match this thing. So it says that that tells you, I just gave you a very pedantic, complicated proof that the sum of 2 convex functions is convex because it matched this rule, with h being the sum function. Okay? How about the max? Same story. The max of a bunch of functions, I mean the max of the max of entries of a vector is convex, and it's non-decreasing in every argument, so it matches this first rule. Everybody got this? So this is actually kind of cool. I mean, I actually recommend that you learn and think about these rules. That's great. They're special cases, but it is kind of cool that there's actually only one rule. Also, if you program in a real language, an object-oriented language, right, which will be, some of you will go, I presume, even before the workshop's over, you'll start learning Julia and Python, right? But anyway, if you do, then you'll realize that when you look at this, in a modern language, this maps into code like instantly, right? So these are just very simple things where you just, if you have an expression tree, you just walk the tree, you look at each of your arguments, you look up the monotonicity and stuff like that. So what's kind of cool is this is just math, but it is slow. It's so close to actionable computer science, it's not funny. I mean, it is literally, you'll look at the code for these things, it'll be identical to this. Okay. All right, so let's do some examples. Here's one. Let's show that this function, f of uv, is u plus 1 log u plus 1 divided by min uv. Now, who the hell knows where that would ever come up, right? But it could, so there it is. And we're going to show that that thing is convex, right? So what we're going to do is this. We're going to start with the variables. We're going to say these are variables. And so u plus 1, actually what I'm doing now is I'm taking the parse tree of this, and I'm going down to the leaves of the tree. And at the next level up, I have sub-expressions like u plus 1, u plus 1, that's the same one. And then I have min of u and v. So let's look at those. U plus 1 is affine, because it's a variable, linear plus a 1. That's affine, that's affine. This thing is concave, because it's the minimum of two affine things. It's going to be concave. So this is concave. Okay. Now we're going to go one step up in the parse tree, in the expression tree, and we're going to observe that the function x log x over y, that's convex in xy, and it's decreasing in y. If I increase y, this goes down, and this goes down. It's monotonic. Therefore, it says generically the following is true. An affine, if I can replace x here with an affine function and y with a concave function, any concave function, and the result will be convex. And that's our function. Everybody got this? So, oh, by the way, if you're curious, like when we were going to do something, we've already done some. This is real stuff. So, I mean, if you've never seen this stuff, there's no way you could absorb all this right now. But if you're curious if we're going to ever do it, if you were curious 20 minutes ago if we're going to ever do anything, I can tell you right now we've done something. So, okay. Let's look at some examples. The log sum x function, that's convex and increasing in each argument. That tells you that if you have a function, f of x and omega, if that's convex in x for each omega, and gamma is positive, it says that the log of the sum of these things divided by k is convex. But that's exactly this. That's the log of the expected value of e to the gamma f of x, where omega here, omega has, it's uniform on these values. And that's actually, this immediately tells you that we can do all sorts of cool inequalities that are widely used in stochastic optimization, because you have log of the probability that this is bigger than 0 is less than this thing. We even saw that early. I remember seeing it earlier today. So, and now what you know is that this thing right here is actually a convex function of x. These things are just not obvious, like even remotely obvious. They're known by some people. You know, you get the right person in statistics, and they'll tell you, I mean, this is something close to like a moment-generating function, and the right people would know that. Actually, they would, right? Because for a moment-generating function, you'd ask a statistician, what's the Hessian? And they would say, oh, that's the variance. Variances are typically, very, very often, they're positive semi-definite, right? So now if you know the Hessian is positive semi-definite, you know the function is convex, right? So there are other ways to know these things, and some people would know them. But here we're just using this one rule, composition rule. Oh, and a set of atoms. Okay. So now we're going to formalize all this. What we're going to do is we're going to do constructive convexity verification. And so that's going to work like this. You're going to start with a function given as an expression. So it's given as, it's a composition with little bits and pieces of things and so on. And then we're going to build the parse tree for the expression. And the leaves are going to be variables or constants and parameters. And then the nodes, every node is going to be a sub-expression. And it's going to have the highest level. It's going to be associated with a function that the function is used to combine the children into the result of that node, right? It could be a unary node, right? It could be a single function of a single argument. Or it could be binary or whatever. So, okay. And the idea is these functions follow that general rule. So what we're going to do is we're going to make this expression tree, and then we're going to walk the expression tree, and we're going to tag every sub-expression from the leaves on up as affine, convex, concave. Okay? So that's the idea. And in fact, you can even do something more sophisticated. You can tag the signs of these things. That's the square is non-negative, the exponential is non-negative. And then you could actually have a slightly more sophisticated thing where you'd look at a function and you'd ask, I could say, if your first argument, for example, is non-negative, what can you say about the monotonicity? And you might be able to say, oh, in that case, it's increasing. The square is a good example. Okay? All right. And what you're going to do is, to turn this into actually something that does this is trivia. It's an undergrad. I mean, undergrads don't know the math, but undergrad computer science stuff, this is like less than a project. I mean, it's a little tiny thing to do this. This is 10, 15 lines in a real language. And what you end up with is something that gives you a sufficient condition for convexity. It's not necessary, but it's sufficient, right? So that's the idea. We're going to look at some examples. Okay? Here's our example. It's x minus y squared over 1 minus max xy. And so you just walk from the bottom up to the top, and you argue the different parts in this parse tree, the different sub-expressions, either convex, concave, or affine. Okay? And I won't go over the details, but I'll just show you this. This is, again, this was done when, I think, so Stephen Diamond was maybe, I don't know, let's just say a sophomore or junior, undergrad. So he just made up a, this is actually running. You can go to dcp.stanford.edu. It should work. So you just go to it. And what it'll do is you can type in an expression. It's just to teach these rules. It has no other function. It does absolutely nothing, right? So you go there. And we've typed in this function right here from the example. Here. So we typed it in. And this is the parse tree. And then what's happened is at every node, we flag things like, on the right is flagged the sign over here, right? So, whoops. I guess I have to, this thing's been getting a little bit flaky. So here, you tag the sign. So plus minus means you don't know the sign of that thing. Here's one. We know the sign of that. Let's find another one. Here. We know that this is positive, this whole thing, because it's something squared divided by something positive, right? Then on the left, we flag, what's flagged is the curvature, right? So the curvature, these are variables, right? And so the little line like that means it's affine. You take the max, and the max of 2 affine is going to be convex, right? Here, you subtract these, you get something that's affine. You do quad over ln here, and here the first argument is affine, and the second argument is concave. And of course, it looks up in quad over ln. It asks, are you convex in your, are you convex? It is. Then it says, what do you know about your first argument? Actually, you don't even have to because it's affine. And then the second argument is concave. And then it says, are you decreasing in your second argument? And it comes back and says yes, and you get this. So you do this, right? So actually, if you're curious, you should just go to this because it also has a quiz mode. So you can actually, it'll generate random expressions, and it'll be your job to figure out if under DCP it's convex, concave, or affine, and then, I don't know, you'll answer and then it'll say right or wrong and show you the parse tree. Okay, so, okay, everybody got this? So, all right. Now, by the way, it can fail, although it's not really a failure. I mean, it can just fail to show something is convex. It obviously is. This is obviously convex. It's the norm of x1, right? It's obviously convex. But it doesn't work because it doesn't, this will throw an exception. It doesn't match the general rule because you had 1 in x squared, that's convex, and there's no rule that says the square root of a convex function is anything. And in fact, there are square roots of convex functions that are nothing, right? That have like multiple bumps and stuff. They're neither convex nor concave. Okay, so, but you can always write it this way, right? And then it's convex. So, by the way, it's very interesting. A lot of, this is actually a good point for me to say something about this. The point of a system like this is not to analyze arbitrary expressions. That's not the point. The point is to give you a way, an extremely small set of rules, in fact, one rule. And if you follow that one rule, then two things happen. Number one, you will only construct things that are convex or concave, number one. And number two, which is going to be the interesting part, is we're going to be able to canonicalize that into a cone program. We'll get to that. Okay. All right. So now we're getting to disciplined convex programming. So we'll see what this is. So the idea is it's a framework for describing optimization, convex optimization problems, and it's basically just going to be an implementation of constructive convex analysis. So you get a sufficient but not necessary condition for convexity, and it's used in a bunch of tools that do this kind of stuff, right? So I'll show you what these are. And by the way, if you are trained in computer science, what you're about to actually see I'm telling you I'm describing a language. This is actually essentially the Backus-Naur, syntax description of what this is. So it's this. A DCP consists of the following. It has 0, 1 objective, and an objective can either be minimize a convex expression or maximize a concave expression. And it can have 0 or more constraints. And these have to have the form convex less than concave, concave bigger than convex. I mean, that's just silly. By the way, when you have convex less than or equal to concave, you subtract the concave from both sides, and you get convex minus concave less than 0. Minus concave is convex, and so convex minus concave is convex, and so, okay. But this is maybe easier to do. Or you can have affine expression equals affine, okay? So this is, and again, if you're trained in computer science, this modern ones, you would actually see things that look exactly, the actual source code that would do this kind of stuff would look just like that. I mean, it would be almost no more lines, okay? Okay, so an expression that's going to be formed from variables, constants and parameters, and functions from a library. And the library functions have to have implemented various methods that tell you about things, right? They have to have known curvature, they have to have known monotonicity, and they have to have the right, the known sign patterns, right? And then the rule is that any sub-expression you build has to match that general rule. So that's the thing. It's actually just one rule. And so that if we have something like that, then you'd say it's called a DCP, a disciplined convex program. What it is it's convex by construction. In other words, it doesn't allow you to build a non-convex problem, right? And it's actually very, very different from like posterior convex analysis. So a long time ago, I had a student, and so he did a lot of computer science stuff. So he said, well, I'll work on detecting convexity of an expression or something. And so we would, he had very clever ways for proving symbolically convexity of an expression, right? And he came to my office one day and he wrote some horrible thing on the whiteboard. It was had hyperbolic tangent and logs and all sorts of crap in it. And we looked at it and he said, did you know that was convex? And I'm like, nope, I didn't. And we kind of both looked at this expression, and after a while, we said, that's cool. Then we both thought about it for a while, and then we both realized it's totally useless. I mean, what? The whole point is not to check if, this would encourage kind of the monkey at the typewriter thing, right? Where you say, here's my problem, is it convex? And supposing it were and it was your lucky day, you wouldn't know why it is, right? So the point is actually, the difference between a posterior analysis also, by the way, as a practical thing is terrible. Because what if I write down a scheduling problem, and this thing analyzes it and says, hey, it's convex. I go, fantastic, I'm gonna field it. Then what happens is somebody runs in and says, quick, we're going to implement a new thing, or we're going to add a new constraint, or we're going to do this, or a new term in the objective. And now it's not, and you have no idea why, right? So the point is it's not even a good idea in practice, right? Because it's not maintainable. So that's the idea. Okay, so. And the cool thing is it's basically based on, it means it's syntactically convex, because in fact, it's so dumb, it knows no math. It doesn't know any math at all. All it knows, for example, you could switch the square root and the fourth root because their attributes match. They're both non-negative, they're both increasing, and they're both concave. It doesn't matter. You could change exp and the positive part, and it would work. Okay, so this is the idea. Okay, now I'm not going to go into this, although it's not actually that hard to do. But it turns out it's very easy to write a DCP parser. In a modern language, it's like 8, 10 lines. I mean, that's it. That's the whole thing, right? Maybe a little bit more, 50 at the absolute most. What I'm not going to tell you about is that if you have a DCP parser, it's not that hard to write a canonicalizer. And a canonicalizer will take that problem, parse it, verify convexity, then it will actually, like a modern compiler, it will then put out an equivalent cone program. Okay? So this is, at the highest level, this is what happens, right? Although it's not much hard. I mean, it's like 50 lines, 60, 80 lines in a modern language, right? Then the idea is you solve the cone program using a generic solver, and it looks like magic, right? So this is like what CVX does. But now you have a modeling framework for doing these kinds of things. Okay? So we're going to look at a couple of these just to show you how it works. But the idea behind a modeling language is this. They're basically domain-specific languages for optimization, right? So, and the idea is you're going to express it in a high-level form. You're going to declare variables. You're going to form constraints and object, and you're going to solve. The cool part is, what you're really shooting for is you want your code to specify the problem to look like the math. That is the goal, right? So the closer they come, actually often the code is shorter and clearer than the math, which is kind of embarrassing, but that sometimes happens. Okay. Now the idea of a language for optimization, that's super duper old. This is from the 70s. And one of the people who worked on that was Brian Kernighan, who's the co-developer of like the C language. So these are not slouch. These are people who know a lot, right? This is, I think, a general algebraic modeling. I don't know. By the way, these are both commercial. So, and these have no support at all for convex problems, right? It's just for specifying your problem. Okay, and these are callable from but not embedded in other languages. They're standalone, weird commercial things. So, okay. But here's some others. There's been a string of them, all based on these ideas from DCP. YALMIP, you have to know, that's a historical reference, which probably a lot of people don't get. So it's a reference to, I guess in the 70s or 80s, somebody came up with something called YACC, Y-A-C-C, which is yet another compiler, because everybody was coming out with a compiler, and so this was YACC. So this is yet another LMI, like pre-parser or something like that. So CVX was, we put together. These are relatively more recent, and they're in real languages like Python and Julia, so that means they're much shorter and much more elegant. So, I mean, CVX has been used by zillions of people, so that's been shaken out pretty well. But these are all open source, so you can look at, poke around inside. These will be very, very, this one especially is like embarrassingly short. But there's a long history of these things, and I'm not going to go into them. But we'll just take a couple of, we'll take a peek at some examples though. So this one we saw last time, but now I can say what happens here. So here, things like a variable is always in the scope of a problem, and a problem starts with a CVX begin and a CVX end. So actually, how many people have used CVX at some point? So, okay, well, that's a fair number. We could ask why the others haven't, but I won't. Okay, so the idea is, so the variables live between, variables, expressions, everything lives in the scope of a single problem, right? This declares the variable. This tells you what to minimize. Subject to, you know what the subject to does here? Anybody want to take a guess? Somebody probably knows, but do you know what the subject to does in CVX? What does it do? Yeah, it looks like it introduces the constraints, right? I'll tell you what it does. Ready? Absolutely nothing. This does nothing whatsoever. It's there only so we can write it so that this looks more familiar to you. So that's it. You could write it anywhere. You could write subject to, norm x int less than 1, and then you could write subject to again. Wouldn't make any difference. So, okay. So you don't need it. Okay. So what happens is here, when this is being processed and it gets here, the problem is canonicalized and then solved, right? And what happens is, if it was feasible, this variable x, which is an object in this scope, is actually overwritten with a numerical x. So it's MATLAB-ish, right, in style. Okay. And here would be some of the functions in that library, right? You'd have the norm, p-norms. the square. I mean, these are sort of obvious things. Here's sum largest. Oh, by the way, you can do sum largest of x in 3.5. What do you think that means? What's the sum of the 3.5 largest entries of a vector? It's convex, by the way, but what is it? Yeah, that's what it is. It's the sum of the largest 3 and half of the 4th. Exactly, yeah. That's convex function. It's not obvious, but it's true. So, okay. And you'd get various other things. Here's our quad over ln friend, and here's lambda max. And this would tell you some of the attributes. Okay. In CVX, the way it works is it's actually being, the DCP analysis is being done as it's being processed line by line. And so you declare some variables, and then you have a constraint. It correctly recognizes that as convex. It correctly recognizes that as concave. And then it says convex less than concave. That's cool. So it accepts it. And the next line, we write max of xy equals 1. And that's a violation. Because for one thing, the only kind of equality constraints you can have are affine. Right? So I could put over here x plus y equals 1. That I could write. But I can't write this. I could write max of xy less than or equal to 1. That would work. Because that's concave less than or equal, convex less than or equal to concave. But you can't write this. And so what will happen is you'll get this. It'll say discipline convex programming error. You can't have convex equals real constant. Okay? So this is just to show you kind of how it works. Okay. CVXPy is written in Python. Oh, and I get to say something else. So tonight, there's actually, later, today, there's this talk on Python. So by the way, those of you who have this deficiency, you can correct it tonight. Or you can start on the path to recovery tonight. What time is that? It's at 7. So it's 7 o'clock. Please come. I was very happy to see that. By the way, one of the things that the person's going to talk about is it's going to talk about something called IPython notebooks, which are things that include beautiful documentation. Even if people give whole talks this way, and the talk is actually an executable Python script. So I should add that most of the things I'm talking about here, everything, all of the source code is in an IPython notebook, all of it. So you can even follow on these things this way. Okay, so, all right. So here's what this looks like. This says import CVXPy. Then this says, create a variable. This creates a variable object. Then it says, form the cost, and that's an expression. By the way, you could use this cost in another problem if you want. No problem. Here, this says construct a problem. We saw that before. And then this says call the solve method on that problem. Right? This is sort of basic object-oriented stuff. And so the interesting thing here are that variables, expressions, and constraints, they're outside of the problem. They're not inside. Right? They're actually legitimate objects. Okay. And this would have, the usual kind of things. Here's the Huber function, which is like a square function up to a threshold, which is like, maybe 1, and then it becomes linear, right? So that's a superb thing to use for robust model fitting. Okay. And DCP analysis, everything works outside of a problem. So you just say x is a variable, y is a variable. I form an expression, which is this thing. This was our example before. And then what you do is you call the curvature method on expression, and it'll come back and it'll say it's convex. Okay? You can call the sign method on it, and it'll say it's positive. And then you can say, is it DCP, which is it known to be either convex, concave, or affine? And it will say, yep, it's true. Right? So all of this you can do there. So, okay. Now, CVXPy also includes parameters, right? So, and a parameter is exactly what it sounds like. In fact, if you think about what the basic mathematics is of what's an optimization problem. So, well, let's start this way. What's the best algorithm to solve an optimization problem? Sounds like a sensible question, doesn't it? Turns out it's an incredibly stupid. Here's the answer. Ready? It's the following program. Ready? It should write the answer. Right? So It's a nonsensical, it makes no sense to say what's the best algorithm to solve this problem. The answer is the one that simply writes the answer out, right? So what you really meant to say was something like this when you want to know what's the complexity or what's the right, you really want to say, I have a family of problems here, like linear programs or, you know, things that maximize mutual information or something. And there's parameters in it, like you haven't said what the channel is, for the channel statistics. And then you'd say, now, what's the best algorithm that solves any instance from that family? That's actually what you're interested in, right? So parameters are actually part of the basic thing. Okay. So the idea is you make a parameter, and then you could do something like this. This would be a very, very simple way to make a trade-off curve, right? This says, you're using the NumPy package or whatever, and this says, you know, make me 100 values from, you know, 1e minus 4 to 100, right? And then it sets gamma to this, gamma dot value, that's the parameter in here. And then what you do is you'd solve, the problem. This does not reparse, it just actually, when you call the solve method, every parameter, if a parameter is not assigned when you call the solve method, it'll throw an exception and it'll say, you didn't instantiate your problem, right? So you instantiate a problem by assigning a value to the parameters, right? And so that's what this does. All right. And then it gets the answer, and what it does is this will overwrite on x dot value the new optimal thing, and then this just puts it on a list, right? So that's a trade-off curve. But here's the cool part. You could do something reasonable like this. It wouldn't look so bad in MATLAB. Here's what's cool. Because this is a real language, where MATLAB is not, it's a real language. So there's actually real toolboxes that do stuff, and we're not talking about stupid little like signal processing toolbox or crap like that. We're talking about the real thing. So what happens is you just import the multiprocessing. There's many like this, and you import, you know, from this like the pool. You import pool, and then what you do is you make a function. It's very simple. It's just a function that maps a value of the regularization parameter to an optimal x. And so it does exactly that. It just takes an argument like this. It sets this equal to this. It solves it, and then it returns the value. So it's completely readable. Okay. Now, you need to know this, that a map does the following. A map, in general, right, it applies a function to a list of things here. So it would apply the getX function to this list, right? And so, you know, this is just if I remove this pool.map but said map, it would be getting the Python base map, and it would simply go through and it would look at each of those values and solve it. Everybody got that? So that's all it would do. But here, I'm using the pool.map, right? Pool is an object, which is, here I instantiated a pool of processes. This is get me capital N processes. And then the pool.map actually runs the map and it does it in parallel. So this will do it on capital N. By the way, this is the entire code. I mean, it's like one or two more lines or whatever. That's it. And you're actually doing serious parallel computing, right? So just like that. So the things like this you could not possibly do in, you know, MATLAB. I mean, any more than you could do it in Excel, right? So, okay. Convex, that's in Julia. And it looks very similar, so I'm not going to go through very many things here with this. I mean, I think we've seen a lot of this. So, and I'll wrap up this part this way. So the idea is that this DCP, or disciplined convex programming, that is, it's a formalization of constructive convex analysis. Constructive convex analysis means you have a library of atoms, and you have a bunch of rules that allow you to combine atoms. And in fact, that's actually a lie, because you don't have a bunch of rules. You have one rule. Actually, there's only one, which, by the way, means that the code that implements this is shockingly short and clear, right? Which, by the way, means it has a very high probability of being correct, right? So if you you can imagine amateur implementations where it says, oh, if you see max, you know, do this. If you see log sum x, do that. You know, things like that will never work. Things that are written in 50 lines and are based on, you know, high-level abstractions, those work, right? So, okay. So this is like a simple method to certify a problem as convex, which is cool. It's sufficient but not necessary. And it's the basis of several DSLs and modeling frameworks. Now, these modeling frameworks make rapid prototyping easy. What's cool I think what's very cool is, we implemented things like this, a long time ago, and it was a pain in the ass, right? It's like a big, it was a serious programming exercise. In modern languages, it's not. These are undergraduate exercises, right? If I can walk up to not a random undergraduate, but I can walk up to an undergraduate and say, make me a parser for this. Here are the rules. I just showed them these slides. It'll be done in 2 hours. Whole thing. I'd say, here's my library. Make a parser for it. It's just, these are just so simple to do, and the code will be clear and short. Anyone will understand it. It's just really nice. Okay. And the references, again, you just go and you type anything into Google, and you're going to get some relevant stuff. Okay. So you survived. We just covered a huge amount of material in this, but hopefully maybe just the flavor of what we covered should stick with you. It's actually pretty straightforward. I mean, the things are not obvious. The atoms are not obvious. The rules it's not obvious that there's one rule, only one rule you need to know. That's it. What we're going to do now is, if people have questions about this is the right time to ask them. Yeah. Yeah.
And maybe not even different code from two CPUs. You need to run
Absolutely.
that code, right?
Sure.
What about running like a cluster or running on a cluster of a server cluster or on GPU?
First of all, this will work. This will work on a cluster.
Okay.
Yeah, no problem. It'll work.
Other types of power processing.
Yeah. So GPU, not yet, but these are things we're working on to make things like this happen. I mean, that would be great. But yeah, but this will work. I mean, I think this uses MP. It's built on MPI. This one. I mean, I don't know the details. This is just one package, right? This is just. So the point of this is, you shouldn't take this too seriously. The point of this is just to show, if you program in a real language, that would be the rest of you, by the way. If you program in a real language, you can actually do real things in 5 lines of code that's on it. This is not. By the way, this is actually the code. This is not the slidified code. Right. So that's all this means. You could make a much better implementation. But this will run on and MPI works just fine. Yeah.
For the whole composition analysis, some complex functions have associativeness. You can have the parse tree is not unique. You can have different order splits.
Yep.
So can you have cases where you're lucky and your splitting shows you that this is convex, or cases where you're unlucky and the split doesn't show you anything?
So that doesn't happen. But we actually haven't done anything sophisticated like that. No, we fix the precedence of how you make the parse tree, and then we just analyze that one thing. That's it. And so if you write things in the wrong order, it won't work. But actually, I don't think we have anything in these things where you flip the order and it works. Did I answer your question?
No.
Okay. Okay. Well.
So maybe for some of the trials you missed, if the result tells you, I don't know if it's convex, and if you try to flip the order, it will tell you it's convex.
Right. So I'm actually trying to think about, give me an example of something like that, because I actually don't think that issue comes up in DCP. I think, right? Because the flipping of the order is basically you're permuting the arguments of the parent function, right?
No.
No. Okay.
You're like if you have a sum of a lot of things, you can bunch them.
Sorry. Oh, yeah. Okay. Oh,
Order of the
sure. No, we don't do anything smart like that. Absolutely none. So that's why this issue does. Okay. So let me give you. Now I got it. Now I can answer your question. You're going to be You're not going to like the answer. The answer is we don't do anything sophisticated at all. If you write, I'll give you one right now. Ready? You have to listen. X squared, minus 2x squared plus 3x squared. Okay? So, yes, if you put the parentheses around a pair of those, it'll work, and if you put it around the other two, it won't. That's what you're talking about? Excellent. I'm close to answering your question. Now I can answer your question. We don't do any of that. We could, but we don't. We actually like it to be stupid, actually, a little bit. I mean, it's kind of charming, right? Would you really want someone to would you want to, let's put it this way, would you like to get into a vehicle where the person who wrote the code that's running relied on on putting the parentheses in the right place or something? All right, that's weird. Okay, I take it back. All right, okay, fine. At least I finally understood your question. So, any more? Okay, all right. So, what we're going to do now is we're going to go to, what we're going to do now is we're going to go into some applications, and you are going to get to choose. We could probably do even just one. And it'll be whatever it is, it's going to be fun, and you get to choose. We're not going to vote, but if people have some idea about these, I could tell you a whole lot about pretty much everything there is to know about portfolio optimization. 15 minutes, we could do that. We could do regression variations. That's really cool. Anybody going to say anything? Which one? We could do worst case risk analysis. That kind of requires the portfolio optimization. So it's not, I tell you what, I think for you people, I think we should do, that's more like that's an application. That's an application. I mean, this is cool, I have to admit, but it ties onto that. Let's do this one because it would be it's going to be interesting and you're going to see things probably most of you have never seen. So we're going to do that. I just decided for you if you're noticing. So that was, no, but if someone had said, okay, I really want to do this or that, we would have done it. But, okay. Oh, okay. Okay. This is just, by the way, this stuff we're going to do, this is like just fantastic stuff to know. And not that many people know it. Okay? So super basic. It's really cool. Here it is. So standard regression, everybody, you know what that is. It's just least squares. What? Yeah. Yeah. I don't do that except by reflecting it. Oh, the question was, could the lights showing on them be turned down?
Sure, but I need it for the cameras for Q&A.
Okay. All right. No more cues. Okay. That's it. Don't ask any questions. No, I'm kidding. That's fine. We'll turn it back. All right. Thanks. Okay. So, standard regression. So here's the idea. You're given a bunch of data, and the data consists of a real number, like an outcome, and then a vector, which is the features that you're going to use to guess things, right? And then we want to form nothing but, an affine model. So you want to have a linear combination of these features with an offset, right? And then the residuals, that's going to be yi hat. That's your prediction. That's the actual observation. That's the error, right? And least squares, this goes back to Gauss, says choose that vector and that offset to minimize the sum of the squares of the errors. Okay, that's the year's 1806 or whatever it is, right? That's regression. That's least squares. Okay. If you do this, right, then the mean of the optimal residuals is 0. Of course, right? So, or you could add Tikhonov regularization. So you add this quadratic here. And of course, that means the mean is not 0, and you trade off mean and variance and blah, blah, blah. Okay, right? So everybody knows about this. Okay. Now, we're just going to look at variations on these things, and you're going to learn some things that are actually just actually amazing. And they should be universally used, but not enough people know about them. But here it is. What you do is you replace the square function. There's the square function with this Huber function, and the Huber function looks like this. It's the square up to some transition threshold m. That'd be like right here. And above that, it transitions to linear. Okay? That's the Huber function. It's fine. It's a statistician from the, worked in the 60s and 70s and stuff like that. Maybe later, 70s. I don't know. Okay, fine. Okay, now the idea here is this is going to be the same as this. If this penalty function on your residuals, it's going to be the same as least squares if the residuals are small. But if the residuals are big, it's actually going to be radically different because you don't like big residuals. But there's a big difference between squaring a big residual and just having and linear of it, right? So Ri and Ri squared, when Ri is big, are way different. Everybody see that? And so I'm anthropomorphizing how you solve things. But the point is, if you have, if you do Huber, if you do least squares and you have one big residual, you're going to do a lot to bring that down, right? Because the amount you care, A big residual is contributing big squared to your objective. Okay. So let's look at an example. By the way, then you get a convex problem and blah, 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 and you can type it in 3 lines in any of these systems and you solve it. But let's look at a thing with 450 measurements, 300 regressors. And this is what we're going to do. We're going to generate the data from a true model, a true vector. The x's will just be Gaussian. And then we're going to add some noise here. And then we're going to do something, oh, and let's have a short discussion about outliers. Okay? So an outlier, if all your measurements are like, in the range plus minus 3, and all of a sudden you see a measurement that's like 1e plus 9, well, duh, it's an outlier, right? So a 15-year-old can write a little program that goes through and removes things that are obviously outliers, right? If your outlier, is perturbed so slightly, then it's covered by, if it could plausibly be Gaussian noise, then it's not an outlier, it'll be handled, right? So it turns out the only real issue with outliers is not things that are like really big, because then you can flag them and just remove them. You just go walk through your data set and ask if anything is 10 to the 6 times more than the, 10 to the 6 sigmas out, right? In which case you remove it, or for that matter, 8 sigmas out, right? Fine. So that's not the issue. So the issue is this. What you don't want are measurements that are plausible and completely wrong. That's actually the issue, if you think about it carefully, right? So in this example, we are creating measurements that are completely wrong and utterly plausible. Here's why. If you look at this, what you'll realize that this y has the distribution of y is Gauss, it's 0 mean. So it's got a certain variance. If you flip y, it's the same. It's 0 mean, same variance. So the point is that at least from a probability distribution point of view, distribution of yi and minus yi is the same. Right? So these are exceedingly plausible measurements. They just happen to be completely wrong because the sign is reversed. Okay? So then what we do is the data has a fraction p of non-obvious wrong measurements. Right? Then what you're going to do is we're going to try to recover this the true parameter from the measurements, and we're going to compare that against the Prescient version. In the Prescient version, we tell you which of the measurements we flipped the sign on. Right? That's obviously the best advantage you could possibly have. And so here's what you get. It's actually kind of amazing. So this is the fraction of the entries that we just flipped the sign on. If you are told which ones have been flipped on the sign, you have a huge advantage. You just flip the sign back and do least squares. Okay? If you just do ordinary least squares, this is what happens. This is your relative error, right? So. And, well, duh, if you take 4% of the entries and flip the signs and do least squares, of course you're going to do it. But what's weird is look at the green thing. This is the Huber thing, right? So, by the way, this was not a weird example that we worked at for days to try. This is just like the first stupid thing that was typed in. Here it is on a smaller scale, and it's actually like incredible. Bear in mind that the blue curve is like way up here, way above the building, right? So what it says is, and this is actually extraordinary, this says that it's something like this. You've taken 4% of these entries and you've just flipped the sign on them completely. You now minimize with a Huber function there, and it sails through. It's not doing much worse than as if someone had taken you by the side and said, oh, by the way, here's a list of the entries that we flipped the sign on. Everybody see what I'm talking about here? So this is, by the way, this is kind of typical, and I'd go so far as to say anybody who deals with real data, anyone who fits this characterization, if you deal with real data and you do any kind of regression or least squares fitting, you should be using Huber, period. Someone has to convince me that that's not the case. So a lot of people doing that, so there's a lot of people who need to change. Actually, what it means is anybody who knows this has a huge advantage until everyone is switched over and everybody knows this. So everybody understand what this is showing? You should be impressed.
So this is over like training error?
Actually, it's both. It's fine. No, it'll be the same thing. This is training error. It'll be exactly the same with test. So it's fully real. Also, in this case, actually, we're showing this, so it's not, the training test is not relevant, right? I'm giving you the relative error and actually extracting the exact parameter. So test would be the same. Okay. Any more questions? Everybody got what this is? So, by the way, this is this whole area when people say things like, well, what can you do with convex? This is one of the things you can do with convex optimizations. You can take things that people have done in 50 industries for 50 years, and you can make them like way more robust, like way more, and just automatically, right? So, okay, everybody got this? Okay, we're going to move on. We're going to do quantile regression because it's fun. So here it is. So what we're going to do is, here's a penalty. The penalty is going to go like this. We're going to take the penalty function is going to look like this. We're going to multiply tau times the positive part, 1 minus tau times the negative part. And so that's the same as, half of an absolute value plus tau minus half times u. And depending on what value of tau you get different. Some people call this like an asymmetric L1 norm. It's weird, but okay, here it is. If tau is 0.5, this is the negative part, positive part plus this negative part, that's this, right? If tau is 0.1, you get this. And several ways to think about it. This is tau equals 0.9, you get this. Very cool ways to think about it. If I am going to minimize phi of the residuals, this is basically saying I care equally about overestimating and underestimating. That's what tau equals 0.5 means, right? It's tau and 1 minus tau. This says I care 10 times, it bothers me 10 times more, actually 9 times more. It bothers me 9 times more to underestimate than overestimate. That's what this says. This says it bothers me 9 times more to overestimate than underestimate. Okay, so just from complete intuition, you know what's going to happen now. If I give you a bunch of data and ask you to fit, what will happen is this is going to produce some kind of a model that's kind of guessing in the middle. This is going to produce something that's guessing, this is going to be like the 90th percentile because it does not, it's going to make a high estimate because because you pay 10 times more to be wrong on that, to overestimate. Everybody following this? And this one, again, just pure intuition, it's going to guess low, right? Because guessing high, no, maybe it's the other way. I think I switched, should be the other way around. Okay, this is fine. All right. So quantile regression says minimize this function of the residuals. Now, if you work out what this thing is, it's simple. If none of the residuals is zero, then these functions, which are these piecewise linear things, they have very simple derivative, right? If you're negative, it's one thing. And if you're positive, if you're negative, I guess if you're positive, it's like plus tau, and if you're negative, it's minus tau. And so the derivative is this. All right. Now, roughly speaking, for the optimal v, this has to be 0. It won't be exactly 0, but I mean, if there's an odd number, it will be exactly 0. But what it says is, for the optimal v, these are 0. This thing is 0. That's assuming none of the residuals are 0, but okay. And what that means is, if you work out what it is, it says that m is the total number of residuals, and this says tau times m is going to be the number of negative ones. And this says that when you do this, the tau quantile of the residuals is 0. And that's why this is going to be quantile regression. By the way, this is the same as, this is exactly like 1806 and regression. If someone says when you regress, then they say, tell me about the distribution of your residuals. You can say, well, the mean is 0. On the training set exactly, on the test set, close to it. Okay, everybody got, this says if you do quantile regression and someone says, tell me about your estimates and tell me about how much you're off by. What are the residuals? And the answer would be, well, the 90th percentile is 0, or the 10th percentile is 0, or the median is 0, right? So, okay. So we'll just do an example now. We just make a time series, and we're going to make an autoregressive predictor. Looks like this, so it just says we're going to guess the next entry as a linear combination of the previous m entries and a static offset. And we're just going to use m equals 10. And we're going to use quantile regression for 3 values of tau. What that means is you're solving 3 completely different problems, and you're going to get 3 different estimators. One is going to estimate essentially the 10th percentile. One's going to be the median, and one's going to give you the 90th percentile, right? And so you're going to get, when you run this, you're going to get 3 predictions about the next step, and then of course you can see for yourself where the next step landed, right? And here's the time series. I can't remember what it was. To make it interesting, it's some tiny, it's 2 lines of code. It's some nonlinear, recursion or whatever that does something. But there it is. That's the time series. And your job is to predict, make a prediction of the next entry given the last 10. Okay? So here it is. Here are the predictions. And the cool part, this is the training set. So the cool part is that, sure enough, the blue one, which is like our 90th percentile prediction, is typically above the other two. There are 3 different predictors, right? This doesn't really tell you much. This would be, if you zoom in, it might look like this, right? And it's actually pretty cool because, let's see, I can't remember which is which now. I think the black one is the actual time series. And so what it is that each moment, it's actually quite interesting, like here at time 4:32, if you say, what's the next entry, you say, well, I don't know, but this is my guess, that's my high guess, and that's my low guess. And there's a pretty healthy gap there. But if you're down here at time 4:10 and you say, what's the next element, you say, well, I think it's going to be about 0.4. And you say, what's your high estimate? And you'd say 0.42. And what's your low estimate? You'd say 0.38. Everybody following this? Right? So the point, but we did nothing. We just solved 3 convex optimization, but we didn't do anything, right? It's nothing smart here at all. Well, except you solve the right problems, 3 of them, right? And you get 3 different predictors that will, so actually, I mean, it can even be weird. You can even say things like, oh, it's actually telling you how confident it is in its prediction. But this is the point when Bayesians say this comes for free if you're a Bayesian, but okay. Okay. And you can look at the residual predictions, and it's dead on. The green one was our median thing, and sure enough, these are the actual errors. Your median is 0, right? This is the median. Here's your 90th percentile, and sure enough, that is 0, right? And here's your 10th percentile, right? So this is kind of the idea. Here it is on the training set, on the test set, and you know, it's simple. It's close enough. It gives you kind of what you want, right? So, how many people have seen quantile estimation before? Or quantile predictions or things like this. So, and I think people in statistics have known about this for a gazillion years, but I don't know. It's simple enough. So, okay, everybody got that? So at this point, I think we're gonna wrap up. So I'd be happy to answer questions about this, questions about all of this. We'll take attendance and make sure you go to the Python thing later today. So. Any questions? Yeah.
Since we have 3 different estimations,
Yeah.
can we make sure that it's get a better result?
Can we do what?
Can we do a combination of against these results to get a better result?
You have to define what you mean by get a better predictor. Each of these is optimizing something. And so once you tell me what you mean by a better predictor, the answer is probably yes, we could. So what did you mean by get a better predictor? Closer in what sense? You see? There we go. So are you going to judge it by how often you're high and low? Because then that green one is the global optimum. Are you going to judge it by the sum of the squares of how far? Because then the regression from 1806 is optimal, right? So you have to be much more specific about what you mean by the prediction is close to the value. And sometimes when you articulate something like that, it'll result in a convex problem. But it's a good question. In fact, that's really kind of what this is about. Yeah?
So back to the Huber loss that you described.
Yeah.
So you flipped about less than, let's say, 8% of the values.
Yeah, let's say here.
Yeah. Right.
Yeah.
And you talked before that about if you take a vector and you take the k largest value,
Mm-hmm.
it's convex and the smallest one is concave. What if you just ignored, took just the 90% higher ones and just optimized on those?
So actually, there is a strong connection between Huber and the sum of the k largest. And that goes into something called, I think it's called, it's value at risk, in finance it's called value at risk and conditional value at risk. And it's exactly that, right? So there are connections and you could do that. There's also there's another thing, ransack. Do people know this? Or so there are standard algorithms that would probably do close to this, right? By the way, we could also improve this hugely because you would do something close to what you're saying. The first thing you do is you do a Huber fit. then you go back and you look at your 400 measurements and you ask which residuals were over the threshold and which were under. And now what I do is I throw out the ones that are over and I refit. It'll do way better than this. But that would be 4 lines of code, not 3 or 2. So yeah. So there are lots of other things you could do. And you could go, and there are other methods to do things like this. So this is certainly not the only method that will work. Yeah.
You strongly recommended using the Huber, and how does it compare relative to L1 norm?
Oh.
Split it all the way?
Well, okay, how does Huber and L1 norm compare? They're the same for large residuals, right? Because they're both linear, right? So when you do L1 norm, there's actually 2, I mean, this is going to sound really stupid what I'm about to say, but it's true. There's 2 things about an L1 norm that are important. I mean, its behavior when things are small, and it's got that point, and the behavior when things are big, and there it's linear asymptotic growth. So Huber is quadratic for small, and then asymptotically linear, and so Huber and L1 would have similar robustness characteristics to large outliers, right? Now, in L1, you also have this thing where it's sharp point, and that's sparsifying. And that means that so at least in squares, right? Once a residual is small squared is like really small, and you don't even care. So when you do least squares or Huber, you could have a bunch of little residuals, and you don't care, you don't expend the effort to make it, I'm anthropomorphizing, but you don't spend the effort to make it 0, right? Because it's already small squared, right? So there's actually, so when you do L1, you're doing kind of a weird thing, like you're combining robustness to large things, but you also don't like small things or something. You like small things to be 0. By the way, there's a function that is the absolute value, goes out to a threshold, and then goes quadratic. It sparsifies, but it also does not like large residuals, right? It's a Frankenstein function made from quadratic. And you know what it's called? The other one is Huber. That's it. It's Berhue. That's exactly right, yeah. So I've never heard of a legitimate use of it, but it is cool. And so therefore, I'm pretty sure we implemented it in all these libraries just because it's weird and cool. So, but there was actually a question right behind you. Yeah.
Yeah, in CBS Pi,
Yeah.
can you use the constraint of a problem and then change the objective in the loop?
Oh, absolutely. Sure you can. Not even in a loop. You can do it in a map. I just showed you.
Okay.
You can, yeah, sure.
So you can change the parameter in the objective.
Yeah, you can do anything you want. Parameters you're free to change arbitrarily. I could change anything. I could do, for example, this. I could solve a problem and then I can say constraints plus equals and then add a constraint. Did you understand what I just said? Okay. So for the rest of you, it means that I just added a constraint to my problem and then solved it again. So I could write a cutting plane code in like 5 lines. So yeah, that's the point.
But that only in CBS Pi, not in CBS MATLAB, right?
No, you could not do that easily in those. You could do something like it, but it'd be a pain in the ass, but you could do it. So, yeah. Yeah. Sorry, actually, I'm sorry, I can't, you have to speak up.
Do you have any plans to develop the software into the Spark Apache so that I can
Oh, that's a good question. Yeah, so people have been talking about all sorts of things, either in Spark. Actually, the other one that it's bits and pieces are being implemented in. Well, I can tell you what they are. The other one is what's one? Yeah, GraphLab. But then also there's the big machine learning ones. But that's the Spark Apache thing. But there's several efforts going on, and so hopefully something like that will happen. But GraphLab is one. Yeah, those have been kind of disappointing so far, but we'll see what happens. Oh, and the other big one, and I just say this just in case there's some weird person here who wants to do this, because so many people, you would be so popular you can't even imagine, is actually to make a native R implementation of something like this. If you did that, you would have so many statistician friends you can't even believe it. You may not want that, but think it through carefully. But I know so many. You have no idea how popular. You'd be more popular than you can ever imagine, right? I mean, yeah, more than like resolving a whole bunch of conjectures and information theory. Like you'd be way more popular than if you did that. So, I'm just You know, because someday somebody's going to stand up and says, hey, I know math, I know R, this looked pretty easy, I can do it. Because I don't think it's that big a deal, but it is just going to take someone who really knows R. Let's put it that way. So there's no one here. Are you volunteering? That's fantastic. Oh, that's great. Okay. Yes, sorry.
So given that the Huber functions and other loss functions were known in the statistician community, it's not recent, right?
It's what? I'm sorry, what?
I mean, it's not recent. It's been around for some time.
Yeah, sure.
So why has that not caught on?
I think it's a complicated thing. I mean, part of it for a lot of these things is that there are people who, you know, things that were useful enough. You have books written about this in the 60s and 70s. What they didn't realize at that point is that, sure, there's no analytical solution of something like Huber fitting. You know, duh, there's no. But they still thought, they got caught up in, you know, and then you write a chapter, multiple papers on how to solve it. And then, of course, everyone's going to ignore it if you have some stupid algorithm that says you have to do this and you read through this thing. I mean, so I think the barrier to entry now is way lower because you literally write in like 0.2 times the pos of R plus 0.8 times, you know, the pos of minus R. I mean, you literally, and then you write sum around that and then you write minimize and you're done. So I think the whole point there is that it's much easier now to do this. And so the barrier to entry is much lower. And I actually honestly believe that's why it hasn't propagated. Because, I mean, just imagine it's 25 years ago, or it's now, and you just live under some rock somewhere, and no, but seriously, suppose you have a real job, like you work at a hedge fund or something, and you're an economist or you do econometrics, and you want to predict something, and you have data and you fit. You've been using least squares like everybody has since 1806, right? And then someone comes to you and says, oh, no, use this. It's way better. If any of the data's wrong, this is what, how do you do it? And you're like, oh, no problem. You'll need to first install this quadratic programming software, and then let me show you this algorithm, and let me prove that it works, and blah, blah. And you're like, thanks, but no thanks. You know. So I actually really think that's why it is. It's because people made it too damn complicated. And it's not complicated. I mean, it is if you look at all the detail. You can make it complicated if you like, but it's not. I think the right way to say it is, it's a convex problem, trivially transformed to a cone problem and solved. So, yeah.
Do you see that solving this new problem helping us in getting a better understanding of the analytical properties?
So that's a good question. So actually yeah. So the question was, the ability to actually numerically solve these problems, has that been helping people advance the analytical understanding of the problems? That was the question, right? Yeah. So the answer is yes. So that's happening in a lot of different, in statistics. I mean, my colleagues there do all this L1 stuff, and some of them don't care. They know that it works really well in practice. Others do care and start looking at stuff, but a lot of it is empirically based. And empirical means that they're solving problems all the time. And then that'll lead them to conjectures, and then they go off and prove it and stuff. So I would say yes, that's happening. Yeah? Oh, how you solve a cone program? Yeah. So it's a whole area. I could tell you. It's not that complicated. But I think I won't, if you don't mind. And actually, so I used to do this I'd go, and if I were talking about an application, like in control, I'd say, okay, here's the problem. We just solve it. And then immediately, like everyone, like, how'd you solve it? Did you use, like, conjugate gradient? You used, augmented Lagrangians. I bet you did. Or did you take gradients? I'm like, finally, actually, what I started doing when people would ask stuff like that is I'd look at them and say, none of your goddamn business. And then they'd get infuriated. And I'd say, doesn't matter. It's a convex program. I can tell you 50 totally different ways to solve it. Every single one would work. I used one of them. But if I'd used another, the results would be the same. So the idea is I actually like this idea that of me refusing to tell you how we did it. But I can tell you this, that's for a good reason. It's because I can think of 10 different ways, and they would all do it. And you'd get the same plot, if it's correct. I mean, it matters for efficiency. Yeah, but that's the question, how long did it take you? That I would answer, if someone asked me. Don't you want to ask me how long this took? Oh, I had to use the UCSD supercomputer, and it took about a week and a half. No, the whole thing probably took about, I don't know, 300 milliseconds for all of them. But yeah, okay, it's good. So yeah, and of course it matters what method. Or it matters if you want to scale it, right? You can't type these things in. You can't go to Google and say, oh yeah, or you can't go to like Walmart and say, give me last week's point of sale data. Okay, now I'm going to fit a model, and come on. So yeah, so it does matter. It's a really good question. I can tell you later, if you like. Yes.
How much money do you spend on MATLAB licenses?
Oh. Well, I don't know. I mean, it's through the university. I'd like to respond to that question, but I have a microphone here, and that's not a good idea.
Non-zero.
So I'm not going to. Yeah, it's a good question. Yeah, more than we should. But I use it. At CVX is there. I use it. So, but at least I recognize that we should be moving away from there.
Is CVX a toolbox or is it an open source?
No, it's open source. It's an open source thing. Yeah. I don't even know what that means if it runs on some proprietary thing. But anyway. But yeah, it is. Yeah. All right. I am going to declare. Oh no. Where? Oh yes.
I had a question about the first part of the talk,
Yes.
kind of high-level question.
Mm-hmm.
So, given that all these ideas have appeared in statistics, we now see that ideas in convex optimization, we can kind of anticipate these tools that people have known for ages in statistics.
Yeah.
We see these ideas in what we now know as convex optimization, kind of being subsumed by some more general theory.
Oh, yeah, that's a great question. So the question is, are there more general, are there more general theory? And the answer is yes. So probably, if we're going to do this over again, we could go back and look at monotone operators, right? That would be a theory that includes all of convex optimization and frankly, some other extra stuff. So there are theories that expand it. And some of those are all tractable problems, right? But not much. So yes, there are theories that generally, yeah. But the cool part is actually the interplay between the different fields. Like in statistics, they say we know that. We call that that's the moment generating function. We've known that for hundreds of years, right? And then so it's actually, but it's fun. The interplay is fun. I'm talking about the theory stuff. It's fun. All right, I'm going to declare the stopping criterion satisfied.
Very good. So